So now we are going to study the asymmetrical circuit. So in the same thing we are going to study the asymmetrical circuit. So this is the called as the asymmetrical circuit, means here in the one leg there are two thyristors, whereas in the other leg there are two diodes. So these two legs, the components in these two legs are different. So that is the reason we are going to call this as asymmetrical. Asymmetrical means the components in the first leg and the components in the second leg both are different. So because of this only we are going to call this circuit as asymmetrical. And the components in the first leg are T1 and T2, whereas the components in the second leg are diodes, which are D1 and D2. So now we are going to give a single phase supply, single phase AC supply, and here we are going to keep a load. So basically this is single phase semi-converter, which is basically of configuration of asymmetrical. Convert is a rectifier converting AC to DC. So now we are going to analyze this circuit, and this is the load having a load voltage of V0 and the load current is I0 of T, and this is the source current Is of T. So now with this circuit, now we are going to analyze what is the different types of waveforms. So this is the source voltage Vs of T. So Vs of T is equal to Vm sin omega T. So as Vs of T is equal to Vm sin omega T, so this is the graph we are going to get. From 0 to pi is a positive pulse and pi to 2 pi is a negative pulse. And then here T1, the thyristor T1 we are going to trigger at alpha, whereas thyristor T2 we are going to trigger at pi plus alpha, because T1 is going to conduct only in the positive cycle of the supply voltage, whereas T2 can be triggered only in the negative cycle of the supply voltage. So because of that reason only we are going to trigger the T1 at alpha, whereas triggering the T2 at pi plus alpha. So now we are going to draw, as I have already assumed that the load current is always a constant current because of inductance load is a very high value. So the load current is always continuous in nature and is a constant value. So now based on this assumption, now we are going to draw the graph of the output voltage. Now the graph of the output voltage now we are going to get in this manner. So from alpha, I have already told you we are going to trigger the T1. As we are going to trigger the T1, by default D2 is also going to get conduct. So therefore T1 D2 are going to conduct from alpha to pi. So from alpha to pi we can say that T1 D2 are conducting, means the output voltage is equal to source voltage. So therefore V0 of T is equal to Vs of T. So whatever the source voltage, it is following the load voltage also. And if you apply the KCL, we are going to get the source current is equal to I0 of T. So same thing, whatever the source current is equal to load current in this range from alpha to pi. From pi to pi plus alpha, still we have not triggered the T2. So it is in the forward blocking mode. So in that range, D1 and D2 are going to conduct, because these having a low resistance because of this only. So the D1 and D2 are going to get conduct. So as D1 and D2 are going to get conduct, so we can say that simply here V0 of T is equal to 0 and the source current is equal to 0. So source current is equal to 0 in this range from pi to pi plus alpha. At pi plus alpha we are going to trigger the T2. At pi plus alpha we have triggered the T2. So we can say simply that T2 and D1 are going to conduct now. So T2 and D1 are going to conduct in this range. So T2 and D1 are going to conduct. So we can say if you apply the KVL, then V0 of T is equal to minus Vs of T in this range. So it will be negative of the supply voltage. So negative of the supply voltage. If voltage is negative means the supply voltage is negative, means negative of that will be positive. So this is the output voltage we are going to get. And from 2 pi to 2 pi plus alpha or 0 to alpha, as the T1 is not triggered, means it is open. So therefore in that range again D1 D2 are going to get conduct. So therefore we can say that here again D1 D2 are going to get conduct. So therefore simply we can say that again output voltage is equal to 0 and the source current is equal to 0. So this is the graph we are going to get. So for the asymmetrical and also symmetrical, both the graphs of the output voltage and the source current are same. They are same as the previous circuit. For the symmetrical circuit and the asymmetrical circuit, both the output voltage and the source current are same. But only thing is the operations of the thyristors and the diodes are going to get changed, but remaining everything is same. So therefore now this graph we are going to call it as the quasi-square waveform. So this is called as a quasi-square waveform. The source current in this asymmetrical circuit we are going to get, whether in the symmetrical or in the asymmetrical, we are going to get quasi square waveform, or simply in a single phase semiconverter the source current is quasi square waveform, whereas in single phase full converter the source current is square waveform. This is the difference here. So now based on this we are going to draw what is the current in the thyristor T1. As I have already told you, the thyristor T1 is going to conduct only from alpha to pi. So in the remaining ranges it is not at all conducting, so it will be 0 in the remaining range, whereas it is conducting only from alpha to pi. So in that range the thyristor current is equal to load current, so therefore it will be I0. Now I am going to draw what is the graph or the current in the diode D1. As I have already told you, D1 is conducting from 0 to alpha and also from pi to pi plus alpha and also pi plus alpha to 2 pi. So in all these ranges D1 is conducting. So except from alpha to pi, in remaining every range D1 is conducting. So therefore in that range, so D1, the current in the D1 is equal to the load current. So therefore simply we can say it is equal to I0 in this range. So therefore we can say that if the value of the current I0 is from 0 to alpha, again from pi to 2 pi the current is I0. So I have already told you the load current is always constant, because we have assumed that here it is basically the load inductance is very high. So because of that the load current is always constant. So now we are going to do some more analysis of this circuit. See here, now I want to find what is the average value of the thyristor current. So average value of the thyristor current. See, I have already told you the thyristor current is the current of the thyristor T1 is conducting only from alpha to pi. So therefore here I0 into pi minus alpha by 2 pi. So this is called as the average value. So if you want to find what is the RMS value, so IT RMS is equal to I0 into under root over pi minus alpha by 2 pi. And if you want to know what is the average value of the diode current, the average value of the diode current is equal to, here diode current is flowing from, for the diode D1 the current is flowing from 0 to alpha, again pi to 2 pi. So therefore overall I0 into pi plus alpha by 2 pi is the average value. And if you want to know what is the RMS value of the diode current, which is I0 into under root over pi plus alpha by 2 pi. So this is the analysis of this circuit. So now if you want to know what is the conduction angle of the thyristor and the conduction angle of the diode, see the thyristor T1 is conducting from only alpha to pi. So therefore the conduction angle of the thyristor is pi minus alpha, whereas the conduction angle of the diode is equal to, which is, here this is alpha and this is pi, so therefore pi plus alpha. So the conduction angle of the thyristor is pi minus alpha, whereas the conduction angle of the diode is pi plus alpha. So this is pi minus alpha and this is pi plus alpha. So let me do some more analysis of this circuit. Here I have already told you from alpha to pi. So from alpha to pi I have already told you we are going to trigger the T1 at alpha. So therefore T1 D2 are going to conduct in the alpha to pi. So as the T1 D2 are going to conduct, so we can say that the output voltage is equal to source voltage and also the source current is equal to load current. So this is equal to I0. Whereas from pi to pi plus alpha, here in this pi to pi plus alpha still we have not triggered the T2. So T2 is open. So therefore D1 and D2 are going to get conduct. So therefore the output voltage is equal to 0 and the source current is equal to 0 in this case. Whereas from pi plus alpha to 2 pi, we have already triggered the T2. So therefore T2 D1 are going to conduct in this range. So therefore if you apply the KVL, we are going to get V0 is equal to minus Vs of t and Is of t is equal to minus I0, which is negative of the source current, which is negative of the load current. Whereas from 2 pi to 2 pi plus alpha or 0 to alpha, still we have not triggered the T1. So T1 is in forward blocking mode or it is open circuit. So because of that D1 D2 are still are going to get conduct, because then only the current will be continuous in nature. So D1 D2 are going to conduct. So therefore the output voltage is equal to 0 and also the source current is equal to 0. So we have assumed that the load current is always constant. So based on this only we are going to get the operations of all these things. So because of inductance is very high. So if you want to know what is the average value of the output voltage, which is 1 by 2 pi into 2 times of integration of alpha to pi Vm sin theta d theta. So if you do this one, we are going to get finally Vm by pi into 1 plus cos alpha, or if the general expression which is 2 into Vm by 2 pi into cos alpha minus cos beta, where beta is equal to pi, we are going to get finally Vm by pi into 1 plus cos alpha. So in any way we are going to get the same result. I have already told you the conduction angle of the thyristor is pi minus alpha, whereas the conduction angle of the diode is pi plus alpha. So now there is a difference of conduction of thyristor and diode. So from this also we can say that it is asymmetrical circuit because the conduction angle of thyristor is not equal to the conduction angle of the diode. So because of this also we can say it is a asymmetrical circuit. Freewheeling diode connected across load. If any freewheeling diode connected across load, then replace D1 D2 by freewheeling diode and analyze. But graph of V0 of t and Is of t and I0 of t is still remain same. See, suppose if you are going to keep any freewheeling diode across the load, then here we must replace D1 D2 by freewheeling diode, and the graph of V0 of t, Is of t and the I0 of t are going to remain same. But only thing is now we are going to get the variation. We are going to get the variation of the conduction angle of the thyristor and also the conduction angle of the diode. They are going to get vary, but everything is same. So now we are going to study the full wave bridge plus freewheeling diode is equal to semi-converter. So in the semi-converter we have learned the two circuits which are the asymmetrical and also symmetrical. So now we are going to study the another thing which is the combination of full wave bridge rectifier plus freewheeling diode. Means in a full wave bridge rectifier, if you keep a extra freewheeling diode, then this overall is going to behave like a semi-converter. It's a very important point here. If you are going to keep the full wave bridge rectifier plus, and if you add some extra freewheeling diode, then the whole circuit is going to behave like a semi-converter. So therefore you can see this is, see, except this freewheeling diode, the remaining circuit is same as the full wave bridge rectifier. So now I am going to keep an extra freewheeling diode for this circuit. So this now overall circuit is going to behave like a semi-converter. So now we are going to see here. See, this is the source voltage Vs of t and this is the source current Is of t, and this is the load voltage plus or minus V0 of t, and this is the load current I0 of t. And I have already told you here we are going to assume the load is having a huge value of inductance. So therefore the current is constant here. It is not at all changing. So it's always constant with respect to time. And this is the source current Is of t. So T1, T2, T3 and T4. So now we are going to analyze the diagrams of this circuit. So this is the source voltage Vs of t. So Vs of t, the source voltage is in this fashion, which is from 0 to pi it is having a positive pulse, from pi to pi it is having a negative pulse. So Vs of t is equal to Vm sin omega t. So the peak value of plus Vm and minus Vm. So now we are going to trigger the T1 and T2 at alpha, whereas triggering the T3 and T4 at pi plus alpha. So triggering T1 and T2 at alpha and triggering T3 and T4 at pi plus alpha. So this is the gate current, gate pulse current we are going to give for T1, T2, and this is for T3 and T4. So now here at alpha we are going to trigger the T1, T2. See, at alpha we have triggered the T1, T2. Then what is going to happen basically? Then as a T1 and T2 are going to conduct, so therefore the output voltage is equal to source voltage, and also the output current, the source current is equal to output current. So therefore here from alpha to pi the output voltage is equal to source voltage. So it is going to follow the source voltage. Whereas from alpha to pi here the output voltage means the source current is equal to output current, which is I0. Whereas from pi to pi plus alpha, the voltage want to try to become negative in the full wave bridge rectifier, but there is a freewheeling diode. So because of this freewheeling diode, so because of negative voltage, this freewheeling diode is going to get conducted by default. So therefore now as the freewheeling diode is going to get conduct, so output voltage is equal to 0. So therefore here the freewheeling diode is going to get conduct. So because of this reason only here the voltage is equal to 0. But in the full wave bridge rectifier here also T1 and T2 are going to conduct. But in this case the freewheeling diode is going to get conduct. So because of that pi to pi plus alpha the freewheeling diode is going to conduct. So therefore the output voltage is equal to 0 and the source current is equal to 0. Whereas from pi plus alpha to 2 pi, I have already told you at pi plus alpha we are going to trigger the T3. So T3 and T4 we are going to trigger at pi plus alpha. So because of that here if you apply the KVL, the output voltage is equal to negative of the source voltage. So go for the negative of the source voltage. And simply here if you apply the KCL, the source current is negative of the load current. So negative of the load current we are going to get in this region. Again from 0 to alpha. From 0 to alpha, the voltage want to be try to be negative because in the previous full wave bridge rectifier, T3, T4 are going to get conduct. But here freewheeling diode is going to conduct. So because of that, again the output voltage is equal to 0 and also the source current is equal to 0. So you can see clearly these are the output voltage and the source current of the semi converter. So these are the graphs which are present in the semi converter. So therefore we can say that full wave bridge rectifier plus freewheeling diode is called as a semi converter. So because of this reason only, because the output voltage and the source current are the graphs which are same as the asymmetrical and symmetrical circuits graphs. So this is called as the full wave bridge rectifier plus freewheeling diode combination is called as the semi converter. So because of this reason only. I have already told you the load current is always constant with respect to time. I am assuming its value is I0 for all the time. So based on this, I want to draw what is the graph of the thyristor current and the diode current. So I want to find what is the current in the thyristor T1. So what is the current in the thyristor T1? So you can see clearly T1 is conducting from only alpha to pi. Only from alpha to pi, the thyristor T1 is going to conduct, and the remaining regions the T1 is not at all conducting. So we can say that simply here only from alpha to pi T1 is conducting. So therefore whatever the current in the thyristor is equal to current in the load. So therefore its value is I0. And in the remaining regions T1 is not conducting. So therefore it is going to act like open circuit. So current in that region is always equal to 0 in the remaining range. So now I want to find what is the current in the diode. Let me assume the freewheeling diode. See what is the current in the freewheeling diode I want to figure out. See, the freewheeling diode is conducting from 0 to alpha. Again from pi to pi plus alpha it is conducting. So therefore we can say only from 0 to alpha and pi to pi plus alpha it is conducting. So whatever the current in the freewheeling diode is equal to load current. So it is again load current. So these are the graphs of the current in the thyristor and the current in the freewheeling diode. So now you can see clearly the conduction angle of the thyristor in this case is pi minus alpha, whereas the conduction angle of the freewheeling diode is 2 alpha. So the conduction angle of the thyristor is pi minus alpha, whereas the conduction angle of the freewheeling diode is 2 alpha. So let me do analysis of this circuit. So whatever the circuit we have known, which is the full wave bridge rectifier plus combination of freewheeling diode is equal to semi converter. So for this now we are going to do further analysis. See from alpha to pi, I have already told you T1 and T2 are going to get conduct. So therefore the output voltage is equal to source voltage and also the source current is equal to output current. Whereas from pi to pi plus alpha, the freewheeling diode is going to get on. So therefore the output voltage is equal to 0 and also the source current is equal to 0. Whereas from pi plus alpha to 2 pi, so T3 and T4 are going to get conduct. So therefore the output voltage is the negative of the source voltage, whereas the source current is equal to negative of the output current, which is minus I0. So whereas from 2 pi to 2 pi plus alpha or 0 to alpha, again freewheeling diode is going to get conduct. So therefore the output voltage is equal to 0 and the source current is also equal to 0. So because of this only, the output voltage and the source current are the graphs which are same as the semi converter. So that is the reason we are going to call the full wave bridge rectifier plus freewheeling diode as a semi converter. And I have already told you the conduction angle of the freewheeling diode is 2 alpha, whereas the conduction angle of the thyristor which is pi minus alpha. And if you want to know what is the circuit turn off time of the thyristors, so circuit turn off time of the thyristors, let me take for T1. So for T1, say from 0 to alpha, it is going to have a positive, it is in the forward blocking mode, whereas from alpha to pi, it is conducting, whereas from pi to 2 pi, the source voltage is negative, so because of that, it is under reverse bias. So only negative voltage can apply across the thyristor T1 from pi to 2 pi. So therefore the circuit turn of time is equal to pi by omega is the circuit turn of time. Is this is the time for which the negative reverse voltage is going to apply across the thyristors. So now I want to find what is the thyristor average current. See, in the thyristor only it is connecting from only alpha to pi. So therefore I naught into pi minus alpha by 2 pi. And if you want to know what is the RMS value of thyristor current, which is I naught into under root over pi minus alpha by 2 pi. And if you want to know what is the diode average current, which is I naught into 2 alpha by 2 pi. And if you want to know what is the RMS value of diode current, which is I naught into under root over 2 alpha by 2 pi. And I want to tell you the average value of the output voltage is equal to 1 by 2 pi into 2 times of integration of alpha to pi Vm sin theta d theta. So finally we are going to get Vm by pi into 1 plus cos alpha, or it is twice the average value of the half wave rectifier. So therefore we are going to get the general formula, which is 2 into Vm by 2 pi into cos alpha minus cos beta. Here beta is equal to pi. So therefore we are going to get finally Vm by pi into 1 plus cos alpha. It is the average voltage across the output. Now let us do the comparison of all the semiconductors. So in the semiconductors we have learned the first circuit is symmetrical, and in the second circuit we have learned the asymmetrical. In the third circuit we have learned the full wave bridge rectifier plus freewheeling diode. So these are the three circuits that we have learned in the semiconductor concept. So now we are going to compare all the thyristor currents and the diode currents. So the thyristor current, the thyristor average current in the symmetrical is I naught by 2, whereas in asymmetrical it is I naught into pi minus alpha by 2 pi, whereas in the full bridge plus freewheeling diode is called as the I naught into pi minus alpha by 2 pi. Whereas the ITRMS in the symmetrical circuit is I naught by root 2, whereas here I naught into under root over pi minus alpha by 2 pi, whereas here I naught into under root over pi minus alpha by 2 pi. Whereas the average value of the diode current is I naught by 2 here, and here it is I naught into pi plus alpha by 2 pi, whereas here it is I naught into 2 alpha by 2 pi. Whereas the RMS value of the diode current, which is I naught by root 2 here, and it is I naught into under root over pi plus alpha by 2 pi in the asymmetrical, and it is I naught into under root over 2 alpha by 2 pi. So if you know the basic concepts, then you can usually figure out the average value, RMS value of the thyristor current and also in the diode current of each and every circuit. So these are the values for every symmetrical, asymmetrical and the full bridge plus freewheeling diode. So these all the circuits are going to come under this semiconductor. So each and everything is basically a semiconductor. So in all above three circuits, V0 of t and Is of t have same waveforms. I have already told you in the asymmetrical, in the symmetrical and also in the full wave bridge rectifier plus freewheeling diode, in all these circuits we have got the same type of waveform of the output voltage and the same type of waveform of the source current. So source current in the semiconductor is always quasi square waveform, whereas in full wave bridge rectifier the source current is square waveform. So now we are going to find what is the average value. Means for the semiconductor, the output voltage and the source current. Now we are going to do some more analysis for the semiconductor. So the average value of the output voltage is equal to here 1 by 2 pi into 2 times of integration of alpha to pi into Vm sin theta d theta. So if you do this one, we are going to get Vm by pi into 1 plus cos alpha. So this is called as the average value of the output voltage of the semiconductor, which is Vm by pi into 1 plus cos alpha. Whereas if you want to find what is the average value of the source current, so if you want to find what is the average value of the source current, so from alpha to pi it is going to have a plus sign or whereas from pi plus alpha to 2 pi it is going to have a minus I naught, and the remaining ranges it is 0. So simply we can say that the source current average value is equal to 0. Whereas if you want to find what is the source current RMS value, which is I naught into under root over 2 times of pi minus alpha by 2 pi, or after simplifying we are going to get I naught into under root over pi minus alpha by pi. So this is basically a periodic waveform. So now we can write in terms of Fourier series. We are going to get the is of t is equal to sigma n is equal to 135 up to infinity 4 I naught by n pi into cos n alpha by 2 into sine of n omega t minus n alpha. So here you have to go for, see in the previous one, the source current expression in the previous, which is full wave bridge rectifier, which is sigma n is equal to 135 up to infinity 4 I naught by n pi into sine of n omega t minus n alpha. Whereas here the extra factor which is here, keep a division of 2 here, and here cos n alpha by 2. Everything is same. So here n alpha by 2, take the same term, keep a cos here. So cos of n alpha by 2, and remaining everything is same. So sigma n is equal to 135 up to infinity 4 I naught by n pi into cos of n alpha by 2 into sine of n omega t minus n alpha by 2. So this is the only difference with respect to the full bridge rectifier. So is of t is equal to sigma n is equal to 135 up to infinity 4 I naught by n pi into cos of n alpha by 2 into sine of n omega t minus n alpha by 2. So this is called as the source current. So now I want to find what is the fundamental component of the source current. The fundamental component of the source current means keep a value of n is equal to 1. We are going to get 4 I naught by pi into cos of alpha by 2 into sine of omega t minus alpha by 2. So this is called as a fundamental component of the source current, which is is1 of t. It is called as the fundamental component of the source current. So now I want to find what is the fundamental displacement factor. The fundamental displacement factor is the cause of angle between the the source voltage and the fundamental component of the source current. So here we can say simply cause of angle between the fundamental value of the source voltage and the fundamental value of the source current. So because of that, here we are going to get cos of alpha by 2. So alpha by 2 is the angle between the, see, Vs is nothing but Vm sin omega t, whereas the fundamental component of the source current is, this is the expression. So angle between them is alpha by 2. So cos of alpha by 2 is called as the fundamental displacement factor. Whereas distortion factor is equal to, I have already told you, it is the ratio of the RMS value of the fundamental source current by the overall RMS value of the current. So now I want to find what is the RMS value of the fundamental component of the source current, which is 4 I naught by pi cos of alpha by 2 by root 2, peak value by root 2, whereas the source current RMS value is just now we have figured out, which is I naught into under root over pi minus alpha by pi. So if the simplification of these things, we are going to get 2 into under root over 2 by 2 into root 2 by root over pi into pi minus alpha into cos alpha by 2, whereas the distortion factor in the previous full bridge rectifier, it is equal to 0.9. It is independent of the alpha, whereas it is depending upon the value of alpha. So you can see clearly the distortion factor is equal to 0.9 in the case of full bridge rectifier, whereas here it is depending upon the value of alpha. Whereas in full bridge rectifier it is independent of alpha, whereas in the semi-converter it is depending upon the value of the alpha. Alpha is called as the firing angle. So therefore G is equal to 2 into root 2 by under root over pi into pi minus alpha into cos of alpha by 2. So THD is equal to, so total harmonic distortion is equal to under root over 1 by G whole square minus 1. So you know the value of G, substitute here, and if you do simplification, finally we are going to get under root over pi into pi minus alpha by 8 cos square alpha by 2 minus 1. So this is the value of the THD, whereas the THD in the full wave bridge rectifier, which is 48.43%, it is independent of the value of alpha, whereas in the semi-converter it is depending upon the value of the alpha. So now I want to find what is the value of the input power factor. It is a product of the distortion, or you can say distortion factor into fundamental displacement factor. So input power factor is the product of the distortion factor into fundamental displacement factor. So you know the value of G and you know the value of fundamental displacement factor. So G is this value and the fundamental displacement factor is cos alpha by 2. So if the product of these two things, so we are going to get this formula. So this is the formula we are going to get. So if you do the simplification, because cos 2 alpha is equal to 2 cos square alpha minus 1. So therefore cos alpha is equal to, so cos alpha is equal to 2 cos square alpha by 2 minus 1. So by using the simplification, finally we are going to get under root 2 into root 2 into by under root over pi into pi minus alpha into 1 plus cos alpha. So this is the final expression we are going to get. So you can see clearly input power factor is also depending upon the value of the cos alpha or alpha function. Whereas in the input power factor is input power factor in the full bridge converter, which is 0.9 cos alpha. There it is 0.9 cos alpha, but here it is root 2 by root of pi into pi minus alpha into 1 plus cos alpha. So simply after final simplification, we are going to get under root over 2 by pi into pi minus alpha into 1 plus cos alpha. So this is the thing we are going to get. So I have already told you the range of alpha is from 0 to pi. So now we are going to find what is the value of the output voltage we are going to get. I have already told you the average value of the output voltage expression for this one is, which is Vm by pi into 1 plus cos alpha. So if you substitute alpha is equal to 0, we are going to get V0 average is equal to 2 Vm by pi. And if you substitute alpha is equal to pi by 2, we are going to get V0 average is equal to Vm by pi. If you substitute alpha is equal to pi, we are going to get V0 average is equal to 0. So you can see as alpha is varying from 0 to pi, so V0 average is changing from 2 Vm by pi to 0. So therefore here it is only in the range of positive, only positive values only we are going to get. As I have always, the load current is always positive, it cannot be negative. So therefore here if you take the coordinate I0 and V0 average, so V0 is always positive and I0 is also positive. So only it is a first coordinate operation. So semi-converter can only operate in the first coordinate, whereas the full converter, the full bridge converter can operate in both first coordinate and also in the fourth coordinate, whereas the semi-converter can only operate in the first coordinate. And also I have already told you the ripple frequency is equal to the number of pulses into supply frequency. As there are two pulses in the output, of the output voltage waveform, so therefore the frequency of the, or you can say the fundamental frequency of the output waveform is equal to twice the supply frequency, or the ripple frequency is equal to twice the supply frequency. So this basically, this semi-converter is also called as single phase 2 pulse 1 coordinate converter. So it is basically a single phase 2 pulse 1 coordinate converter, whereas the full bridge converter is also called as the single phase 2 pulse 2 coordinate converter, whereas this semi-converter is called as the single phase 2 pulse 1 coordinate converter, whereas the full bridge converter can be called as the single phase 2 pulse 2 coordinate converter, whereas this semi-converter is called as the single phase 2 pulse 1 coordinate converter. So if you want to find what is the RMS value of the output voltage, I have already told you, which is under root over 1 by 2 pi into 2 times of integration of alpha to pi Vm sin theta whole square d theta. So if you solve this one, finally we are going to get Vm by under root over 2 pi into under root over pi minus alpha plus sin 2 alpha by 2. So this is called as the RMS value of the output voltage. So now we are going to do the comparison of the fully controlled converter and the semi-controlled converter or semi-converter. So fully controlled converter or the semi-controlled converter. So now we are going to do the comparison of these two things. So average value of the output voltage for this one is, which is 2 Vm by pi cos alpha, whereas for here which is Vm by pi into 1 plus cos alpha. So and the fundamental component of the source current, which is here for this one, which is the RMS value of the fundamental component of the source current, which is here 2 into under root over 2 by 2 root 2 by pi into I naught, whereas here which is 2 root 2 by pi into I naught into cos of alpha by 2. Whereas the source current RMS value for here it is I naught, whereas here I naught into under root over pi minus alpha by pi. Whereas the distortion factor for this case, which is 2 root 2 by pi is equal to 0.9, whereas here which is root over 2 by pi into pi minus alpha into cos alpha by 2. Whereas the fundamental displacement factor for this case, which is cos alpha, whereas for here it is cos alpha by 2. Whereas the input power factor is equal to, for this case, which is 2 root 2 by pi into cos alpha, which is the product of the distortion factor and the fundamental factor. So input power factor is the product of the distortion factor and the fundamental displacement factor. So we are going to get 2 root 2 by pi cos alpha, or simply 0.9 cos alpha. Whereas here we have to do the product of these two things, and if you do simplification, finally we are going to get under root over 2 by pi into pi minus alpha into 1 plus cos alpha. So this is the expression we are going to get finally. And the THD is equal to, for this case, which is 48.43%, it is independent of alpha, whereas here it is a function of alpha. I have already told you the complex one. So this is a very complex equation. So we have did all the comparison of each and everything for the full converter and also the semi converter. We are going to start the single phase full wave controlled RE load. So for the single phase full wave controlled, here we are going to keep the load as RE load, and then we are going to analyze the circuit. So single phase means we are going to give the single phase supply, and the full wave means in the output we are going to get 2 pulses. Full wave control means here we are going to use all the thyristors. So full wave control means we are going to use all the thyristors. Half wave control means we are going to use the combination of thyristors and the diodes. Whereas full wave control means we are going to use only the thyristors. And RE load, the load we are going to keep it as RE load. So here we are going to use the load as RE load. So therefore this is the source voltage Vs of t, and this is the source current Is of t, and the load voltage is plus or minus V0 of t, and the load current is I0 of t. So based on this, now we are going to analyze what is the output voltage and also the output current. So this is the source voltage we are going to get, which is Vs is equal to Vm sin omega t. So from 0 to pi it is having a positive pulse, whereas from pi to 2 pi it is going to have a negative pulse. So with a peak value of plus Vm and minus Vm. So this is the source voltage. I am going to assume the value of E is always lesser than the peak value of the source, which is E is less than Vm. So this is the E value we are going to get if you draw the line. So here, see, we can only trigger the thyristors only when the source voltage is greater than E. Then only there will be a positive voltage across the thyristors. So therefore, but at the value of theta 1, so theta 1 is called as theta 1 is equal to sine inverse of E by Vm. So if in this range only from theta 1 to pi minus theta 1, only in this range we can say that the source voltage is greater than the value of E. So therefore we can simply say that only in this region we can trigger the value of the T1 and T2. So therefore here the alpha can lie only from theta 1 to pi minus theta 1 if you want to trigger the T1 and T2 in this case. So at alpha, the range of alpha to trigger the T1 and T2, which is theta 1 to pi minus theta 1. Similarly, for if you want to trigger the T3 and T4, then you have to go for this one, which is pi plus theta 1, and this 2 pi minus theta 1. So only in this range, which is pi plus theta 1 to 2 pi minus theta 1, only in this range we can trigger the T3 and T4, because only in this region then only we are going to get a positive voltage across the thyristors, then only we can trigger them. So therefore alpha can vary from theta 1 to pi minus theta 1 in this range, and we can trigger anywhere between this pi plus theta 1 to 2 pi minus theta 1 for the value of the, if you want to trigger the T3 and T4. So at alpha we are going to trigger the T1, T2, whereas pi plus alpha we are going to trigger the T3 and T4. So alpha can lie between theta 1 to pi minus theta 1 only. So you can see clearly from up to theta 1 everything is reverse bias, or simply we can say the source voltage is lesser than the value of E. So So therefore a reverse voltage is going to apply across the T1 and T2. So therefore they are open circuit. So whatever the output voltage is equal to the voltage across the E value, and the output current is equal to 0 in this case. Whereas from theta 1 to alpha, here we are going to miss, even though the source voltage is greater than the value of E, they are in the forward blocking voltage. They are in the forward blocking mode because we have not given the triggering. So therefore we can simply say they are still open circuit. So therefore the output current is equal to 0 and the output voltage is equal to E. So output voltage is equal to E and the output current is equal to 0. Only from alpha we have triggered the value of T1, T2. So we have triggered the thyristors T1 and T2. So they are going to get on. So therefore now the output voltage is equal to the value of the source voltage and the output current is equal to, we can simply say that the output current is equal to output voltage minus E by R. So now here it is going to follow the source voltage. So T1 and T2 are only conducting from alpha to pi minus theta 1. So only in this range it is going to act like a whatever the output voltage is equal to source voltage. So the current in the load is equal to V0 minus E by R. So therefore V0 is equal to here in this case, which is Vm sin omega t minus E by R in this case, only from alpha to pi minus theta 1. So at pi minus theta 1, so Vs is equal to E. So because of that again current is equal to 0 here. So this is the graph we are going to get. For after pi minus theta 1, the source voltage is less than value of E. So therefore T1 and T2 are in the reverse blocking mode. So therefore they are open. So therefore the output voltage is equal to simply is equal to E and the output current is equal to 0. So this is the graph we are going to get for the T1 and T2 case. Same graph, take the image, or you can take the same image of this one from pi to 2 pi to get the value of the another one. So take the image of this one again. So we are going to get this graph. So simply we can say that same graph we are going to take it. So we are going to fit for T3, T4 also. Simply again from pi to pi plus theta 1, I have already told you we have not triggered the T3, T4. As we have not triggered the T3, T4, they are in the, or we can say they are in the, as the source voltage is lesser than the value of E, so therefore they are in the reverse blocking mode, so they are off. So therefore whatever the output voltage is equal to value of the E value and the output current is equal to 0. So here, whereas from pi plus theta 1 to pi plus alpha, even though the source voltage is greater than the value of E, they are in the forward blocking mode. So because of that only we can say the output voltage is equal to E naught and the output current is equal to 0 here also. Whereas from pi plus alpha we have triggered T3, T4, so they are on. So therefore if you apply the KVL, we are going to get the output voltage is equal to negative of the source voltage, so negative of the source voltage, and the output current is equal to V0 minus E by R. So if you do this one, we are going to get, so this is the graph we are going to get. So this is the graph, this is the graph we are going to get simply. So only up to 2 pi minus theta 1 only we are going to get, because only for this range pi plus alpha to 2 pi minus theta 1 only T3, T4 are going to get. So after that again they are in the, as the source voltage is again lesser than the value of E, so they are in the forward blocking mode, or simply we can say reverse blocking mode. Again they are off. So we can say that here they are, if they are off means again simply the output voltage is equal to E naught E and the output current is equal to 0. So this is the graph we are going to get for this all these operations. So same thing again we are going to do the same analysis. So I have already told you from 0 to theta 1. From 0 to T1, theta 1, see the source voltage is lesser than the value of E. So therefore all the thyristors are in the reverse bias region. So all thyristors are in the reverse bias. So therefore we can say T1, T2, T3, T4 are in the reverse bias. So therefore the output voltage is equal to all are open. So therefore V0 is equal to E and the output current is equal to 0. Whereas from theta 1 to alpha, see even though we have not triggered T1, T2, they are in the forward blocking mode, they are open, and T3, T4 by default they are reverse bias. So therefore again all are open. So therefore V0 is equal to E and the output current is equal to 0. Again from alpha to pi minus theta, so we can say simply that now we have triggered T1, T2, they are in the forward conduction mode, and T3, T4 they are in the reverse bias, means open. So if you apply the KVL, we are going to get V0 of T is equal to source voltage and I0 of T is equal to output voltage minus E by R. So output voltage is equal to source voltage, which is Vs of T minus E by R is the current we are going to get. I have already told you from pi minus theta to pi, again everyone is reverse bias. Again everyone is reverse bias means simply again the output voltage is equal to E and the output current is equal to 0. So same thing again, pi plus theta 1 2. So pi plus theta 1 to pi plus alpha also I have already told you. So again same thing is going to happen, is again everyone is reverse bias. So therefore the output voltage is equal to E and the output current is equal to 0. Again from pi plus alpha to 2 pi minus theta. So now we are going to trigger T3 T4. So they are in the, we can say they are in the forward conduction mode. So therefore but T2 to T1 T2 are the reverse bias. So therefore the output voltage is the negative of the source voltage. So output current is equal to output voltage minus E by R. Plus output voltage is equal to negative of the source voltage. So we are going to get this formula. So again 2 pi minus theta 1 to 2 pi, again everyone is reverse bias. So therefore if everyone is reverse bias, the output voltage is equal to E and the output current is equal to 0. So this is the analysis. So now we need to find in which range T1 is reverse bias. So T1 is reverse bias from, see T1 is reverse bias. So you can see clearly T1 is reverse bias in which region, which is pi minus theta 1 to pi minus theta 1 to, see pi minus theta 1 to 2 pi, this default reverse bias. So pi minus theta 1 to 2 pi, it is default reverse bias. Again to 0 to theta 1 also it is reverse bias. So simply we can say that from pi minus theta 1 to 2 pi it is default, it is reverse bias. And also from 0 to theta also it is reverse bias. So simply we can say that from pi minus theta 1 to 2 pi plus theta 1 it is T1 is reverse bias. So therefore a reverse voltage is going to appear across the T1 from pi minus theta 1 to 2 pi plus theta 1. So omega Tc is equal to, if it is the difference of these two things, we are going to get 2 pi plus theta 1 minus pi plus theta 1. We are going to get pi plus 2 theta 1 we are going to get. So pi plus 2 theta 1 by omega is called as the circuit turn of time. So the circuit turn of time of the main thyristor, which is pi plus 2 theta 1 by omega. So if you want to know what is the value of theta 1, which is sine inverse of E by Vm. So this is the value of angle, which is at this value the source voltage is equal to value of E. Now you can apply the average voltage. So V0 average is equal to I0 average into R plus E. So therefore I0 average is equal to V0 average minus E by R. So if you want to find what is the average value of the output voltage, which is simply we can go for 1 by 2 pi into 2 times of integration of 0 to alpha E into d theta plus alpha to pi minus theta 1 into Vm sin theta d theta plus pi minus theta 1 to pi, which is E d theta. So you can apply this one to get the value of the average output voltage. So after simplification we are going to get 1 by pi into Vm of cos alpha plus cos theta 1 plus E of pi plus theta 1. So this is the average voltage of this waveform we are going to get. And I have already told you the alpha is going to lie only from theta 1 to pi minus theta 1. And also the conduction angle of the thyristor, because the thyristor is going to conduct only from alpha to pi minus theta 1. So T1 is conducting only from alpha to pi minus theta 1. So therefore we can say simply it is pi minus theta 1 minus alpha. So this is the range for which it is conducting. So therefore this is the conduction range of the thyristor. So now we are going to study the single phase dual converter. Single phase dual converter. So single phase dual converter means this is the circuit diagram. Suppose this is the single phase supply. So this is a single phase supply line. So here we are going to take the two lines. So you can see clearly this is called as the, this is called as a full bridge converter. So this is called as a full bridge converter. Here also same full bridge converter, but these are opposite of each other. So this so we can say the diagrams are opposite of each other. So this is like upward and this is like downward. So therefore now here, suppose if you are going to keep a load here in between these two circuits. So in between these two circuits now we are going to keep a load. Let me assume the load is some RL load. So because of this, we can say because of this bridge, the output voltage will be plus or minus V01 and the output current is I0. Whereas because of this bridge, the output voltage will be plus or minus V02 and the output current is in this fashion. So therefore you can see clearly now the output voltage of the first case. So because of the output voltage can be either positive or negative, but the current is always positive. Whereas because of this bridge, the voltage can be either positive or negative, but the current will be in this direction. So therefore we can get the 4 different types of mode of operation. Means we can get 4 types of quadrant. Let me assume this is the converter 1 and this is the converter 2. So V0 average. So V0 average is equal to, here, see here, this is called as the alpha 1 is the triggering angle of this first converter and alpha 2 is the triggering angle of the second converter. So here when alpha 1 is less than 90, when alpha 1 is less than 90 means here we are going to get for this one, for this first converter. So we are going to get V naught as positive. So V naught as positive and I naught as positive. When alpha 1 is greater than 90, when alpha 1 is greater than 90, so V naught is negative. So V naught is negative and I naught is still positive. So we are going to get this range. So because of this converter, we are going to get the first coordinate and also the fourth coordinate. So because of this one. So if you go for this one, the second coordinate, when alpha 2 is greater than 90, when alpha 2 is greater than 90, we are going to get this coordinate, which is V naught is positive and also here I naught is negative. Means we are going to get current in this direction. So in this direction we are going to get. So this is plus and minus. So we are going to get in this fashion. So if alpha 2 is less than 90, then again V naught we are going to get negative, means V naught we are going to get, see, let me assume this is plus minus V naught average. So plus minus V naught and is the current I naught we are going to get. So because the first converter, see, when alpha 1 is less than 90, so this V naught 1 is equal to V naught. So therefore positive region and I naught is always positive. So I naught is always positive. Whereas alpha 1 is greater than 90, so V naught 1 will be negative. So therefore V naught is again negative. So we are going to get negative value. And also simply we are going to get negative value and also the current is always positive. So we are going to get this coordinate. So because of first converter we are going to get the first coordinate and also the fourth coordinate. But because of second converter, so because of second converter, when alpha 2 is less than 90, so when alpha 2 is less than 90, so V naught, see, this plus or minus V naught is always positive. If this is a positive means V naught is negative. So therefore V naught is negative. So this is negative V naught. And also the current will be in this case. So current is again negative. So we are going to get this third coordinate. When alpha 2 is greater than 90 means this V naught 2. So this V naught 2 will be negative, means this is positive and this is negative. If this is positive, this is negative means it is equal to V naught. So therefore it is equal to V naught. So therefore again the current is again negative in this fashion only. So therefore we are going to get this second coordinate. So therefore, so we are going to get four coordinates. The first coordinate and the fourth coordinate because of converter 1 and the second coordinate and the third coordinate because of the converter 2. So this is the mode of operation. I am assuming this plus minus as output voltage and this is output current. So based on this we are going to get the four coordinate operation. Means we can get the average output voltage either positive or negative and the output current can be either positive or negative. We can get in any direction with the help of this single phase dual converter. So all the four modes we can easily get here. So if you apply the KVL in this load, if you apply the KVL in this load, it is plus V naught minus plus V naught again plus V naught. See, this minus 2 plus means plus V naught 1 again plus V naught 2 is equal to 0. So therefore V naught 1 is equal to minus V naught 2. But V naught 1, the average value of the output voltage because of the first converter, which is 2 Vm by cos alpha 1 is equal to minus, whereas the average output voltage because of the second converter at a triggering angle of alpha 2, which is a negative of the 2 Vm by pi into cos alpha 2. So these two equivalents are going to get cancels. The constant terms are going to get cancels. So finally we are going to get cos alpha 1 is equal to minus cos alpha 2. So minus cos alpha 2 you can write, which is cos of pi minus alpha 2. So cos of pi minus alpha 2. See, pi means again it will be cos, but pi minus alpha means it is the second coordinate. The second coordinate only sign and cosec are positive, but cos is negative. So therefore it will be minus cos alpha 2. So therefore minus cos alpha 2 we can write cos of pi minus alpha 2. So this cos are going to get removed. So finally alpha 1 is equal to pi minus alpha 2 means alpha 1 plus alpha 2 is equal to pi. So therefore simply we can say that the summation of the triggering angles of the first converter plus converter 2, see, the summation of the triggering angles of the first converter and also the converter 2, which is equal to pi. So alpha 1 plus alpha 2 is equal to pi. This is a very important statement. So this, based on this, there are so many questions have been asked. So therefore alpha 1 plus alpha 2 is equal to pi. So now we are going to study the three-phase half-wave uncontrolled rectifier. Three-phase half-wave uncontrolled rectifier. So we have successfully completed the single-phase supplies. So now we are going to study the three-phase. So three-phase half-wave uncontrolled rectifier. So uncontrolled means here we are basically use all the diodes. Half-wave means here now we are going to get only 3 pulses in the output. So therefore three-phase means we are going to give three-phase supply. Half-wave means we are going to get in output there are 3 pulses we are going to get, and the uncontrolled means all the devices are now diodes. So rectifier means converting your AC to DC. So three-phase half-wave uncontrolled rectifier, or simply we can we can call it as a 3-pulse converter, because in the output there are 3 pulses. So this is the circuit diagram we are going to get. So this is the diode D1, diode D2 and the diode D3. So these are the 3 diodes D1, D2 and D3. So these are the point A, B and C. So this is the reference point or O. So this is the load we are going to connect, which is the load output voltage or the voltage across the load, which is plus or minus V naught of t, and the current through the load is I naught of t. So this is the point A, B and C. So we are going to keep 3 sources from A to 0 and B to 0 and C to 0. So the three sources, the voltages are VA0 is equal to Vm sin omega t and VB0 is equal to Vm sin omega t minus 120, whereas VC0 is equal to Vm sin of omega t minus 240. So these are the 3 sources we are going to keep across this one. So Va0 is equal to Vm sin omega t and Vb0 is equal to Vm sin omega t minus 120, whereas Vc0 is equal to Vm sin of omega t minus 240. So these are the balanced sources with a phase difference of 180, 120 across each other. So therefore these are the balanced sources. The phase difference of each individual with respect to another is 120 degree. So they are phase difference by 120 degree. So here we are going to get 3 sources. So these are the 3 sources. This is the source 1 voltage, this is the source 2 voltage and this is the source 3 voltage. So we can see clearly they are phase difference of 120 degree across each other. So Va0, Vb0 and Vc0. So we are going to draw the diagrams of Va0, Vb0 and Vc0. So this is the diagram of the Va0 and this is the Vb0 with a phase difference of 120 and Vc0 with a phase difference of 240 with respect to Va0. So this is the diagram we are going to get finally. So now I have split each part into 30 degree. So this is each and everything I have made into 30 degree. So 30 degree, 60 degree, 90 degree, 120, 150, 180, 210, 240, 270, 300, 330 and 360. So these are the, for each and every I am going to make it as a 30 degree to analyze the output waveforms. So these are the diagrams of the Va0, Vb0 and Vc0. They are phase difference of 120 with respect to each other. So V0 is going to come first and then Vb0 is going to come second and then we are going to get Vc0 as the last. So now at any load, suppose irrespective of the load, so irrespective of the load, at any load we are going to get the, or we can say here I am going to assume, see I am going to assume basically a load is of highly inductive. So I am going to assume the load is of basically very highly inductive. So for highly inductive, then I can say that means I am going to assume it's a highly inductive means current will be always constant. Suppose for any load, I have already told you here, see here from 30 degree to 150 degree, Va0 is greater. So if these 3 diodes are going to present, so whatever the peak value means whatever the voltage which is higher, only that diode is going to get conduct. So you can see clearly from 30 degree to 150 degree, Va0 is greater than Vb0 and Vc0. So from this diagram we can see clearly from 30 degree. So simply we can say from 0 degree to 30 degree, we can say that here this Vc0 is greater than Va0 and Vb0. So therefore the diode which is connected to Vc0 is going to get conduct, which is D3 is going to get conduct. So if D3 is going to conduct, whatever the output voltage is equal to voltage across the Vc0. So therefore it is going to follow the Vc0. Whereas from 30 degree to 150 degree, so whereas from 30 degree to 150 degree, we can say that here Va0 is greater than Vb0 and Vc0. So therefore the diode D1 connected across the point A is going to get conduct. So therefore whatever the output voltage is equal to Va0. So therefore, so from 30 degree to 150 we are going to get the voltage, output voltage is equal to Va0. So this is the Va0 we are going to get. Again from 150 degree to 270 degree. So again from 150 degree to 270 degree, we can say that Vb0 is greater than Va0 and Vc0. So again Vb0 is greater than Va0 and Vc0. So therefore we can say that the diode which is connected to Vb0 is going to get conduct. So therefore the output voltage is equal to Vb0. So therefore the output voltage is equal to Vb0. So you are going to get the output voltage is equal to Vb0. Again here you can see clearly, again from 270 degree to 360 degree, again Vc0 is greater than Vb0 and Va0. So therefore simply we can say that the diode connected across the C point, which is the D3 is going to get conduct. So therefore the overall voltage, the output voltage is equal to, which is equal to Vc naught. So therefore it will be Vc naught. Means, see, whichever the voltage is very higher, the diode connected across that point is going to get conduct, and the voltage will be across that diode only. Means, whatever the source connected across the diode will be the voltage across the diode. So therefore across the load. So whatever the voltage across the load is equal to the point where we are going to connect the source across that load. So therefore we can say that, so this is the graph we are going to get finally. So for any load we are going to get, this is the voltage we are going to get for any load. Whereas for R load, suppose if you are going to give basically an R load, then I want to know what is the waveform of the current. So for a R load, the voltage diagram and the current diagram will be in the same manner. So therefore same will be the shape of the current across a R load. So therefore the voltage waveform and the current waveform will be same for a R load, for a resistive load. Suppose for highly inductive load, suppose now I am going to assume a very highly inductive load. So for highly inductive load, the current will be always constant. So therefore here, suppose for inductive or highly inductive load, the current will be always constant with respect to time. So therefore this is the value of I naught. So but the voltage, no matter whatever the voltage, no matter whatever the load, always the output voltage will be in this shape. For resistive load, the current will be same in the format of the voltage, whereas for highly inductive load, the current will be always constant with respect to time. So no matter whatever the load, always here we are going to get the voltage in this format. Whereas for resistive load, always the current waveform and the voltage waveform will be in the same manner. So for highly inductive load, no matter whatever the means always for highly inductive load, the current will be always constant with respect to time. So now we are going to do the analysis of this circuit. So from 30 degree to 150 degree. So from 30 degree to 150 degree, we can say that diode D1 is going to connect, because here VA0 is greater than VB0 and VC0. Similarly, from 150 degree to 270 degree, VB0 is greater than VA0 and VC0. So therefore diode D2 is going to get conduct. Similarly, from 270 degree to 390 degree. So therefore simply we can say that here VC0 is greater than V0 and VB0. So therefore diode D3 is going to get conduct. So therefore you can see clearly each diode is going to connect for a range of 120 degree. So 150 minus 30 is 120, 270 minus 150 is 120, 390 minus 270 is 120. So therefore the conduction angle of the diode is always 120 degree here. So the conduction angle of diode in the circuit is 120 degree. So each diode is going to connect for a period of 120 degree. So now I want to find what is the average value of the voltage. So average value of the voltage I want to figure out. It is simply, you can go like this, which is, so simply I want to find what is the average value of the voltage, which is, see, 3 times of, or simply we can say 1 by 2 pi into, so 1 by 2 pi into 3 times of, so 1 by 2 pi into 3 times of integration of 30 degree to 30 degree to 150 degree. So in this range from 30 degree to 150 degree, the output voltage is equal to VA0. So therefore here, which is VA0 is equal to Vm sin theta. So therefore Vm sin theta into d theta. So V0 average is equal to 1 by 2 pi into 3 times of integration of here 30 degree to 150 degree. Here simply here basically we are going to take output voltage is equal to VA0 in the range of 30 degree to 150 degree. So Vm sin theta into d theta. So if you solve this one, we are going to get 3 root 3 Vm by 2 pi. So 3 into root 3 Vm by 2 pi is the average value of the voltage we are going to get, which is 3 into root 3 Vm by 2 pi. So 3 into root 3 into Vm by 2 pi we are going to get is equal to. So now simply here, so 3 into root 3 into Vm by 2 pi we are going to get the expression. So 3 into root 3 Vm by 2 pi is the average value of the output voltage. So now I want to find what is the RMS value of the output voltage. So RMS value of the output voltage is equal to under root over, same thing, under root over 1 by 2 pi into 3 times of integration of 30 degree to 150 degree. Here same output voltage is equal to V0 in this case from 30 degree to 150 degree. So Vm sin theta whole square into d theta. So if you solve this one, we are going to get root 3 Vm by 2 into under root over 1 by pi into 2 pi by 3 plus root 3 by 2. So this is the RMS value of the voltage we are going to get, which is root 3 Vm by 2 into 1 under root over 1 by pi into 2 pi by 3 plus root 3 by 2. So this is the average or RMS value of the output voltage we are going to get. And if you want to know what is the average value of the diode current. So average value of the diode current is equal to, see already I have told you here I am going to, that each diode is going to connect for only 1 degree out of the 360. So if the, I am going to assume if the load current is constant, if the load current is constant, if I assume for a highly inductive load, then I0 into 120 by 360, then you are going to get I0 by 3. So if you want to know what is the RMS value of diode current, which is I0 into under root over 120 by 360 is equal to I0 by root 3. See, I have assumed that the load is very highly inductive, so therefore the output current is constant. So because of that, we are going to get these values. So I want to find what is the average power absorbed by the load. So average power absorbed by the load, suppose if it is a resistive load, then it is equal to V0 RMS whole square by R. So this is the amount of average power absorbed by a purely resistive load. But if you want to find for a inductive load, then it is V0 average into I0 average, means the average value of the output voltage into the average value of the output current. So if you do the product of these two things, we are going to get the amount of active power absorbed by a inductive load. Whereas for pure resistive load, which is V0 RMS square by R, this is the average value of the power absorbed by a purely resistive load. Whereas for inductive load, it is a product of the average output voltage into average output current. Vm is called as the maximum phase voltage. So Vm is called as the maximum phase voltage. Whereas Vp is called as the RMS phase voltage. So Vp is called as the RMS phase voltage. So RMS phase voltage is Vm by root 2. So Vm by root 2 is the RMS phase voltage, where Vm is called as the maximum phase voltage, whereas Vp is called as the RMS phase voltage, which is Vm by root 2. So VL is called as the RMS line voltage. So RMS line voltage. So therefore RMS line voltage, see the peak value of the line voltage is root 3 Vm. So root 3 Vm is the peak value of the line voltage. So root 3 Vm is called as the peak value of the line voltage. So RMS value of the line voltage is root 3 Vm by root 2, or simply we can say that root of 3 by 2 into Vm. So therefore simply we can say that Vm is called as the maximum phase voltage. So the RMS value of the phase voltage is Vm by root 2, whereas the peak value of the line voltage, which is root 3 into Vm, and the RMS value of the line voltage, which is root 3 Vm by root 2, is called as under root over 3 by 2 into Vm. And also the output frequency is equal to the number of ripples into supply frequency is equal to 3 into Fs, because there are 3 pulses in the output. So therefore the output frequency of the frequency of the output voltage, or simply we can say the fundamental frequency of the output voltage, is equal to 3 times of Fs, where 3 is called the number of ripples present in the output. We can say that here VL is equal to under root over 3 by 2 into Vm. So because of this reason only we have made the simplification. So wherever, see, VL is equal to under root over 3 by 2 into Vm. So we can replace Vm by VL into under root over 2 by 3, then we are going to get these expressions. Replace that VL is equal to under root over root 3 by under root over 3 by 2 into Vm. So if you do the rearrangement, we are going to get in this expression. So this is the way, in the other way of writing the average value, and this is the another way of writing the RMS value. So average value is equal to 3 root 3 Vm by 2 pi, and the RMS value is equal to root 3 Vm by 2 into 1 by pi into 2 pi by 3 plus under root of root 3 by 2 at the rate of 1 by 2. So therefore I have already told you VL is equal to under root over 3 by 2 into Vm. So if you do the replacement, we are going to get either in this format or either in this format. So now we are going to study the 3-phase half-wave control rectifier. So 3-phase half-wave control rectifier, or 3-pulse converter, or M3 converter. So these are the different names of this circuit. So 3-phase half-wave control rectifier. So 3-phase means we are going to give 3-phase supply. Half-wave means here we are going to get only 3 pulses in the output, and here controlled means we are going to use the thyristors. So rectifier means converting AC to DC. So 3-phase half-wave control rectifier, or simply 3-pulse converter, or the M3 converter. So this is the circuit diagram of this one. The only difference is we have replaced diodes by thyristors in this case. So the previous circuit is 3-phase half-wave uncontrolled rectifier, whereas this one is 3-phase half-wave control rectifier. So this is the load. The load voltage is plus or minus V0 of t, and the load current is I0 of t. So now we are going to do the analysis of this circuit. So I have already told you V0. So we are going to give 3 supplies, which are V0 is equal to Vm sin omega t, and Vb0 is equal to Vm sin omega t minus 120, whereas Vc0 is equal to Vm sin of omega t minus 240 degree. So this is the graphs we are going to get. So if you draw the diagrams of VA0 and VB0 and VC0, so we are going to get like this. So V0 is equal to Vm sin omega t and VB0 is equal to Vm sin omega t minus 120 and VC0 is equal to Vm sin omega t minus 240. So this is the diagram we are going to get with a phase shift of 120 degrees between each and every thing. So therefore this is the diagram we are going to get. So for everything 30 degree we are going to draw these lines. So for every 30 degree we are going to draw these lines basically. So now here based on this, so alpha is called as a triggering angle of the thyristors. So the triggering angle of the thyristors can only go from 0 degree to 120 degree. So the triggering angles of thyristors can only go from 0 degree to 120 degree. So this is the range of the thyristors. So therefore the triggering angle of the thyristors can only lie from 0 degree to 120 degree. So now here when alpha is equal to 0, for R and RL load. So for R and RL load, when alpha is equal to 0 means we are going to trigger. So here at 30 degree we are going to trigger T1, and at 150 degree we are going to on the T2, and at 270 degree we are going to on the T3. So therefore we can see that here T1 is going to connect from 30 degree to 150 degree, and T2 is going to connect from 150 degree to 270 degree, and T3 is going to connect from 270 degree to 390 degree. So you can see clearly here, simply we are going to trigger T1 at 30 degree and T2 at 150 degree and TC at 270 degree. So therefore we can simply say that the actual triggering angle of thyristor is with respect to origin, which is 30 plus alpha, and T2 is 150 plus alpha, and T3 is 270 plus alpha. This is the actual triggering angle with respect to origin, whereas alpha can only lie between 0 degree to 120 degree. So now when alpha is equal to 0, so this is the case. So here it will become 30 degree, 150 degree and 270 degree. So T1 is connecting from 30 degree to 150 degree, and T2 is connecting from 150 to 270 degree, and T3 is connecting from 270 degree to 390 degree. So because of that, this is the output waveform we are going to get, which is, see, when T1 is going to conduct, so whatever the output voltage is equal to voltage across the V0. So T1 is connecting means whatever the output voltage is equal to V0. When T2 is going to conduct, whatever the output voltage is equal to VB0. So it is equal to VB0. Similarly, when T3 is conducting, so therefore whatever the output voltage is equal to voltage across VC0. So this is VC0 we are going to get. So these are the graphs we are going to get. So when alpha is equal to 0 for R and RL load. When alpha is equal to 30 degree, then for R and RL load we are going to draw what is the output voltage we are going to basically draw here. So here I have already told you the actual triggering angle with respect to origin for T1 now is going to become 30 plus alpha, which is 60 degree. So at 60 degree we are going to trigger the T1. Similarly, T2 we are going to trigger at 150 plus alpha, which is 150 plus 30 is 150 plus 30 is 180 degree. So 180 degree for T2. Similarly, T3 we are going to trigger at 270 plus alpha, but here alpha is equal to 30 degree. So therefore 270 plus 30 is 300. So therefore simply we can say that T1 is going to conduct from now 60 degree to 180 degree. It is going to conduct, and T2 is going to connect from 180 degree to 300 degree, and T3 is going to connect from 300 degree to 360 plus 60, which is 420 degree. So therefore it is going to connect up to 420 degree. So this is the output voltage. Whenever the T1 is conducting, whatever the output voltage is equal to voltage across the VA0, and whenever the T2 is going to conduct, whatever the output voltage is equal to voltage across VB0, and whenever the T3 is conducting, whatever the output voltage is equal to voltage across VC0. So this is the graphs we are going to get when alpha is equal to 30 degree for R and RL load. So up to 30 we have studied. Suppose if it is more than 30, what is going to happen? Suppose if it is more than 30, what is going to happen? Now we are going to see. See now, suppose if it is more than 30, suppose let me take alpha is equal to 60, which is more than 30. So now we are going to understand this thing. So I have already told you the actual triggering angle of a thyristor T1 is 30 plus alpha. So 30 plus alpha means simply 30 plus 60, which is 90. So at 90 we are going to trigger the T1. And similarly T2 we are going to trigger at 150 plus alpha. So 150 plus 60 is nothing but 210. So we are going to trigger T2 at 120. Similarly T3 we are going to trigger at 270 plus alpha. So 270 plus 60. So we are going to get T30. So T1 we are going to trigger at 90 degree. T2 we are going to trigger at 210 degree and T3 we are going to trigger at 330 degree. So now you can see clearly when T1 is on, whatever the output voltage is equal to voltage across the VA0. So therefore it will be equal to VA0. So it will be up to VA0 up to 180 degree only. So up to 180 degree only it is going to become, see, up to 180 degree only it is going to follow. See, from 90 degree to 180 degree, the output voltage is going to follow the VA0. It is going to follow the VA0. But after that, VA0 is negative. Actually, VA0 is negative. But we don't want negative value because for resistive load, it cannot be a negative value. So therefore, output cannot be a negative value. Because if the voltage is negative, the current will be negative. So current cannot pass in a negative direction across the thyristor. So because of that, we can say that negative voltage is not at all possible. So means it is going to become like an open circuit. So means the thyristor is going to become open circuit, means here the load voltage will be equal to 0. So therefore it will be equal to 0, and also the load current is also equal to 0 in this case. So from 180 to 210 it is going to become 0. Similarly when T2 is going to conduct, then whenever T2 is going to conduct, whatever the output voltage is equal to voltage across VB0. So therefore it is going to follow the VB0. But after 330, after 300, again VB0 is negative in this region. But I have already told you, if V0 is negative, then I0 is negative. If I0 cannot be negative, it cannot pass in the reverse of T2. So therefore it will be open circuit. So therefore V0 is equal to 0 in that case. So in that V0 is equal to 0 in that case. And similarly, when T3 is conducting, whatever the output voltage is equal to voltage across the VC0. So therefore we can say simply whatever the output voltage is equal to voltage across VC0. So it is going to follow the VC0 here also. Here also it is going to follow VC0. But after 60, here actual VC0 is negative. But I already have told you, if VC0 is negative, then V0 is negative. If V0 is negative, current is negative. So current cannot be negative because it is flowing in the reverse direction of T3. So therefore it cannot happen. So it is going to become open circuit, or it is going to become reverse bias. T3 is going to become reverse bias, means open circuit. So therefore V0 is equal to 0. So therefore this is the diagram we are going to get. So therefore this is the actual diagram of the output voltage we are going to get. Means only up to 30 degree. Whether R load or the RL load, then for R load or the RL load, we can say the output voltage is continuous for R load and RL load up to 30 degree. But after that, after 30 degree, for R load only, it is going to become discontinuous. Only it is going to become discontinuous only for the R load. So you can see some type of gaps here, 0 voltage or discontinuous mode we are going to get only for R load whenever alpha is greater than 30. So remember, whenever alpha is greater than 30 degree, for pure resistive load only, there will be discontinuous mode of output voltage we are going to get. Whereas if you take RL load, same thing here. For alpha is equal to 60 degrees, same case as the previous one. Suppose if you are going to take the RL load, and I am going to assume that I0 is very constant. So I0 is very constant means it is always a constant value. So because of that, same diagram we are going to get, same analysis of this same circuit, same analysis as the previous one. But only thing is here, in the previous case it cannot be negative, but now it can be negative. It can be negative in this region because here it is always conducting, means until T2 is triggered, T1 should conduct. So therefore it is going to follow whatever the voltage across the T1, means whatever the voltage across V0, it is going to follow here. And similarly, whatever the voltage across VB0, it is going to follow here. And whatever the voltage across VC0 is going to follow here. Means simply we can say that as the current is a constant value, means it should always conduct. Whether it is a positive voltage or the negative voltage, it should always conduct. So therefore that is the reason when I0 is always constant. So we can simply say that for RL load, no matter whatever the alpha, the output voltage is always constant. But when alpha is greater than 30 degree, only for pure resistive load, we are going to get a discontinuous mode of operation in the output voltage. So now we are going to do the analysis of this circuit. If alpha is equal to 0, I have already told you T1 is connecting from 30 degree to 150 degree and T2 is connecting from 150 to 270 degree and T3 is connecting from 270 to 390 degree. So you can see clearly, if you go for difference of these things, 150 minus 30 is 120 and 270 minus 150 is again 120 and 390 minus 270 is 120. So when alpha is equal to 0, thyristor and the diode both are same. So therefore, if alpha is a triggering angle, means for some non-zero value of alpha, then T1 we should do the triggering from 30 plus alpha to 150 plus alpha, and T2 we should operate only from the region of 150 plus alpha to 270 plus alpha. Similarly, T3 should be operated from 270 plus alpha to 390 plus alpha. So V0 of t is continuous for RL load for any triggering angle. For R load, for alpha less than or equal to 30 degree, continuous conduction mode is possible. So I've already told you, for RL load, irrespective of alpha, we are always going to get the continuous conduction mode in output voltage. Whereas for R load, when alpha is greater than 30 degree, then we can say that we are going to get a discontinuous conduction mode is possible only for resistor load at alpha greater than 30 degree. Or for RL load, irrespective of alpha, we are going to get always a continuous conduction mode. So that is the meaning of this one. So therefore, for alpha less than or equal to 30 degree, so for any kind of load, whether it is a R load or RL load, for both the cases we are going to get the same result. So for alpha less than or equal to 30 degree for any kind of load, so V0 of t will be always continuous, whether it can be R load or RL load, it is always continuous. So if you want to find what is the average voltage for this range for alpha less than or equal to 30 degree, so we can say that here 1 by 2 pi into 3 times of 1 by 2 pi into 3 times of integration of 30 plus alpha to 150 plus alpha. So here from 30 plus alpha to 150 plus alpha, the output voltage is equal to V0, which is Vm sin theta into d theta. So if you solve this one, we are going to get 3 root 3 Vm by 2 pi into cos alpha. So 3 root 3 Vm by 2 pi into cos alpha. So this is the expression we are going to get. And Vm is called as the maximum phase voltage. So I have already told you Vm is called as the maximum phase voltage, whereas root 3 into Vm is called as the maximum line voltage. So the easy way of representation is VML is called as the maximum line voltage, which is root 3 into VL. So if you want to find what is the RMS value of the line voltage, which is VML by root 3, which is root over 3 by 2 into Vm. So here Vm is called as the maximum phase voltage and the maximum line voltage, which is root 3 into Vm. Whereas if you want to find what is the RMS value of the line voltage, which is here VML by root 2, is also called as under root over 3 by 2 into Vm. So you can go for the simplification. So by using the simplification, you can write either in this format or either in this format. So this is the general expression, which is 3 into root 3 Vm by 2 pi into cos alpha. So this is the general expression. So the average value of the output voltage only for alpha less than or equal to 30 degree for any load, which is 3 root 3 Vm by 2 pi into cos alpha. Whereas Vm is called as the maximum phase voltage, and VML means the maximum line voltage, which is root 3 into Vm. Whereas the RMS value of the line voltage, which is VML by root 2, is also called as under root over 3 by 2 into Vm. For alpha greater than 30 degree, what is going to happen? It is discontinuous conduction mode only for R load. Only for R load, there will be discontinuous conduction mode. So now I want to find what is the average value. So average value is here simply we can say that 1 by 2 pi into 3 times of integration of 30 plus alpha to 180 degree only. So only we have to go up to 180 degree only. After that it is going to become 0. That is the region 30 plus alpha to 180 degree. So in this region we can see that the output voltage is equal to Va0. So therefore Vm sin omega sin theta into d theta. So if you solve this integration, we are going to get finally 3 Vm by 2 pi into 1 plus cos of 30 plus alpha. So I have already told you the relations between them. So you can go for any of this, we are going to get finally. So 3 Vm by 2 pi into 1 plus cos of 30 plus alpha. Whereas VML is equal to root 3 into Vm, whereas VL is equal to VML by root 2, or simply under root over 3 by 2 into Vm. So thyristor conduction angle. So what is the thyristor conduction angle? So therefore now for alpha less than or equal to 30 degree, I can already tell you that the conduction angle of thyristor is 120 degree. So this is the for alpha less than or equal to 30 degree, each thyristor is going to conduct for a period of 120 degree. So therefore IT average is equal to I0 into 120 by 360, which is I0 by 3, and IT RMS is equal to I0 into under root over 120 by 360. We are going to get I0 by root 3. So simply we can say that, see, this is equal to the source average current and also source RMS current. So whatever the thyristor current is same as the source current. So therefore we can say the source average current and the source RMS current. So whatever the thyristor current is equal to source current. So therefore source average is equal to source current average is equal to thyristor average current, whereas source RMS is equal to thyristor RMS current. So for alpha greater than 30 degree, For alpha greater than 30 degree, I have already told you for RL load, it is always continuous conduction mode. So no matter whatever the alpha, it is always continuous conduction mode. So therefore, the conduction angle of thyristor is equal to 120. So the IT average is equal to IS average is equal to I naught by 3, whereas IT RMS is equal to IS RMS is equal to I naught by root 3. This is same as the that for alpha less than 30. Whereas for R load only for R load, I have already told you for only for R load, it is discontinuous conduction mode is possible for alpha greater than 30 degree. So therefore, when alpha greater than 30 degree, the discontinuous conduction mode is only possible for R load. So therefore, the conduction angle of thyristor is only, it is going to conduct only from 30 plus alpha to 180. Only for this range it is going to get conduct. So therefore, 180 minus of 30 plus alpha. So we are going to get 150 minus alpha. So this is the conduction angle of the east thyristor, which is 150 minus alpha. When alpha is greater than 30 degree only for resistive load. So therefore, if you want to find what is the IT average, which is I naught into 150 minus alpha by 2 pi or 360 degree, and IT RMS is equal to I naught into under root over 150 degree minus alpha by 360 degree. So you can go for these things. So summary. So whatever the things that we have learned in this circuit, the circuit is 3-phase half wave control rectifier. So whatever the things that we have studied, so now we are going to give the summary of these things. Summary for R load. For R load, you can see clearly for R load. For continuous conduction, for R load, I have already told you here continuous conduction is possible only for alpha less than or equal to 30 degree only. Means from 0 to 30 degree. For alpha is lying between 0 to 30 degree only, continuous conduction is possible. So therefore, V naught average is equal to 3 root 3 Vm by 2 pi into cos alpha. And V naught RMS is equal to root 3 Vm by 2 root pi into under root over 2 pi by 3 plus root 3 by 2 into cos 2 alpha. So these are the expressions of the output average value and the output RMS value when alpha less than or equal to 0 to 30 degree for R load only. For R load, only continuous conduction is possible only in this range. So the conduction angle of thyristor is 120 degree. Already I have told you. So IT average is equal to I naught by 3 and IT RMS is equal to I naught by root 3. And the output frequency is equal to 3 times of the supply frequency, because there are 3 pulses we are going to get at the output. So therefore, the ripple frequency is equal to 3 times of the supply frequency. For discontinuous conduction, so discontinuous conduction is possible only for resistive load for a range of alpha lying between 30 to 120 degree. So only for this range, the discontinuous conduction mode is possible. So we have already figured out the value of the average voltage, which is V naught average is equal to 3 Vm by 2 pi into 1 plus cos of alpha plus 30 degree. So this is the voltage we are going to get, average value. And if you want to figure out the RMS value also, you can easily figure out. I have already given the expression also. So but the conduction angle of thyristor also I have already told you, which is it is connecting from only 30 plus alpha to 180. So if you do subtraction, we are going to get 150 minus alpha. So IT average is equal to I naught into 150 minus alpha by 360 degree, and IT RMS is equal to I naught into under root over 150 degree minus alpha by 360 degree. So I have already told you the thyristor current is equal to source current. So whatever the source current average value is equal to thyristor average value, and the source current RMS value is equal to thyristor value RMS current. Suppose for RL load, I have already told you irrespective of alpha, there will be always continuous conduction is possible. So therefore, always continuous conduction for L is equal to very large value. So continuous conduction is possible only when L is equal to large value. So therefore, we can say that the output average value is equal to 3 root 3 Vm by 2 pi into cos alpha for alpha is lying between 0 to 120 degree. 0 to 120 degree. And the conduction angle of thyristor is equal to 120 degree. So IT average is equal to I naught by 3 and IT RMS is equal to I naught by root 3. So this is for irrespective of the alpha for RL load when we have assumed that L is very large. So here also the ripple frequency is equal to 3 times the supply frequency. So here also same thing. The ripple frequency is equal to 3 times of supply frequency. For all the cases, the output frequency is, the fundamental output frequency is 3 times the supply frequency for all the conditions, for all the cases. So finally I can say that for RL load, it is always continuous conduction mode is always possible for 0 to 150 degree for alpha. Whereas for R load, for alpha greater than 30 degree, discontinuous conduction mode is possible only for R load. Now we are going to discuss the 3-phase full wave control rectifier, or simply we can call it as the 3-phase full converter. So 3-phase full wave control rectifier or 3-phase full converter. So 3-phase means we are going to give 3-phase supply, and the full wave means we are going to get 6 pulses at the output, and the control rectifier means we are going to use the thyristors. So simply we can say it is a three-phase full wave control rectifier or three-phase full converter. So you can go for any of the name. So this is a circuit for this one. So thyristors are T1, T3, T5, T4, T6 and T2. So these are the thyristors names, and also there is the load of, so the load is going to have a current of I0 and the load voltage is V0 of T. So we are going to give A, B, C. So these are at these points we are going to give basically a voltages, the source voltages. So therefore now we can see clearly here as VA0 is equal to, so I have already told you, suppose let me assume some reference point A, some reference point O. So let me assume some reference point O. So therefore with respect to this point O, or VAO is equal to, I have already told you, which is Vm sin omega t. So therefore VBO is equal to Vm sin omega t minus 120. So therefore VCO is equal to Vm sin omega t minus 240. So these are the phase voltages, but I want to know what are the line voltages. So VAB, VBC and VCA. So VAB is equal to, which is VA0 minus VB0. So if you do VA0 minus VB0, then finally we are going to get, which is root 3 Vm sine of omega t plus 30 degree. So VAB is equal to VA0 minus VB0. If you do this one, we are going to get root 3 Vm sine of omega t plus 30 degree. Similarly, VBC is equal to VB0 minus VC0. If you do this one, we are going to get root 3 Vm sine of omega t minus 90 degree. Whereas VCA is equal to VC0 minus VCA, VA0 is equal to root 3 Vm sine of omega t minus 210. So you can see clearly these are also has a phase difference of 120 between them with a peak value of root 3 into Vm. So the line voltage is going to have a peak value of root 3 into Vm, whereas the RMS value is root 3 Vm by root 2. So this is called as the line voltages. So now here there are 6 thyristors, 1, 2, 3, 4, 5, 6. So there are total 6 thyristors. So 360 by 6 is called as the 60 degree. So after this, each thyristor is triggered. So therefore, after every 60 degree, we are going to trigger the thyristors, means one after the other at a angle of 60 degree. At a angle difference of 60 degree, we are going to trigger one after the another. So the outer total degree is 360 degree. Out of that, we are going to use only 6 thyristors. So 360 by 6 is called as 60 degree. So after this, each thyristor is triggered. So therefore, the difference between the each thyristor triggering is 60 degree. So now we are going to analyze the graphs in a very detailed manner. So VA0, VB0 and VC0, I have drawn this graph. So I have already told you VA0, VB0 and VC0, which is V0 is equal to Vm sin omega t, whereas VB0 is equal to Vm sin omega t minus 120 degree, whereas VC0 is equal to Vm sin of omega t minus 240 degree. So these are the voltages of VA0, VB0 and VC0. So I have drawn with respect to origin. So therefore, this is phase difference of 120 and this is for phase difference of 240 with respect to origin. So this is the graphs we are going to get. So now I have already told you the alpha is the triggering angle of each thyristor. They can range only from 0 to 120 degree in the case of 3-phase. I have already told this supply. So for 3-phase supply, the firing angle of the thyristors can range from only 0 degree to 120 degree. So now here these are the positive peaks. So in the upper, see there are T1, T3, T5. That is the order. So T1, T3, T5. That is the order you should trigger. So therefore T1, T3 and T5. Similarly, in the down part, we have to trigger the T2, T4, T6. So T2, T4, T6. So we are going to get T1, T2, T3, T4, T5, T6. So this is the manner you should go for the triggering. So for every 60 degree, we have to trigger the another thyristor. So therefore T1, T2, T3, T4, T5 and T6. So this is the general format of triggering. So therefore T1, T2, T3, T4, T5 and T6. So for after every 60 degree, we are going to trigger the another thyristor. So T1, T2, T3, T4, T5, T6. So you can see clearly the difference between the two thyristors triggering is 60 degree. So for every 30 degree, we are going to draw this straight line. So for each thyristor means the difference between the two thyristors triggering is 60 degree. So now here suppose alpha is equal to 0 degree. So at alpha is equal to 0 degree, I am going to see for any load when alpha is equal to 0 means I have already told you that triggering angle of T1 is 30 plus alpha, whereas triggering angle of T2 is 90 plus alpha, whereas triggering angle of T3 is 150 plus alpha, whereas triggering angle of T4 is 210 plus alpha, whereas triggering angle of T5 is 270 plus alpha, whereas triggering angle of T6 is 330 plus alpha. So now if I am going to assume alpha is equal to 0, then T1 is triggered at 30, T2 is triggered at 90, T3 is triggered at 150, T4 is triggered at 210, T5 is triggered at 270, and T6 is triggered at 330. So based on this, here we are going to find what is the per unit voltage of the output. So the per unit voltage of the output we are going to draw for each and every figure. So before that, let me analyze the circuit. So now we are going to analyze the circuit here. So triggering, I have already told you, T1 is triggered as 30 plus alpha, and T2 is triggered at 90 plus alpha, and T3 is triggered at 150 plus alpha, and T4 is triggered as 210 plus alpha, and T5 is triggered at 270 plus alpha, and T6 is triggered at 330 plus alpha. And I have already told you V0 is equal to Vm sin omega t, and V0 is equal to Vm sin omega t minus 120, and Vc0 is equal to Vm sin omega t minus 240. And I have already told you VAB is equal to root 3 Vm sin of omega t plus 30 degree, whereas VBC is equal to root 3 Vm sin of omega t minus 90 degree, whereas VCA is equal to root 3 Vm sin of omega t minus 210. All these things I have already told you. So now here, suppose for alpha is equal to 0, for alpha is equal to 0 for any load, I want to know what is the output voltage I want to figure out. So alpha is equal to 0 means these thyristors are going to become purely diodes, so similar to diode bridge. So now here, now I am going to see from 30 degree to 60 degree. I want to see what is the nature from 30 degree to 60 degree. I want to see what is the nature. So what is the nature of the output from 30 degree to 90 degree? I want to see. So therefore, from the graph, see from the graph you can see clearly that is T1, T6 are going to get conduct. So you can see from 30 to 60 degree. So from 30 to 90 degree, see from 30 to 90 degree, always T1 is triggered at 30, but already T6 is going to get conduct. So therefore, see from 30 we can see that here it is going to get from 30 degree to 90 degree. So T1 is conducting and also T6 is also going to get conduct. So from 30 degree to 90 degree, T1, T6 are conducting. From 30 degree to 90 degree, we can say that T1 and T6 are going to conduct. So when T1 and T6 are going to conduct, what we are going to get? So if T1 and T6 are going to conduct, then we can say that the output voltage is equal to line voltage, which is VAB. So output voltage is equal to line voltage VAB. So VAB is equal to V0 minus VB0. So VAB is equal to V0 minus VB0. I have already told this one. So therefore, simply, if you want to know what is the value at omega t is equal to 30 degree, so V0 is equal to VA0 is Vm sin omega t. So in place of omega t substitute 30 degree. So Vm sin of 30 degree minus of Vm of 30 minus 120. So 30 minus 120 is minus 90. So if you solve this one, we are going to get V0 is equal to Vm into 1.5. So V0 by Vm we are going to take, which is 1.5. So this is called as a per unit. So output voltage V0 by Vm is called as, we are going to take it as per unit, which is 1.5. So simply we can say that here we are going to get at 30 degree we are going to get 1.5. So you can see clearly at 30 degree I have drawn a point which is 1.5 per unit. So now I want to find what is the value at omega t is equal to 60 degree. At omega t is equal to 60 degree I want to figure out. So substitute here omega t is equal to 60. Here we are going to get Vm 60 minus Vm of sin of minus 60. So if we solve this one, we are going to get V0 is equal to Vm into root 3. So therefore V0 by Vm is called as a root 3 per unit. So therefore, if you want to know, this is called as the maximum value. This is called as the maximum value. So maximum value of output is equal to root 3 into Vm. So root 3 into Vm is called as the line voltage or maximum value of the line voltage. See, maximum value of the line voltage, which is equal to root 2 into VL, where VL is called as the RMS value of the line voltage. So therefore, see, this is called as the maximum value of the line voltage. Root 3 into Vm is called as the maximum value of the line voltage. So this is equal to root 2 times the RMS value of the line voltage. So therefore, this is called as root 2 into VL. So root 2 into VL. So now at omega t is equal to 60 degree, we are going to get V0 by Vm is equal to root 3 per unit, and this is the maximum value. We can say clearly at omega t is equal to 60 degree, we are going to get V0 by Vm is equal to root 3, and this is the maximum value for alpha is equal to 0 degree. So now I want to analyze from 90 degree to 150 degree. So I want to analyze what is the waveform from 90 degree to 150 degree for same alpha is equal to 0. So from 90 degree to 150 degree, I can say that T1 and T2 are going to get conduct. T1 and T2 are going to get conduct. So therefore, if T1 T2 are conduct, so therefore then output voltage is equal to So output voltage is equal to VAC. So output voltage is equal to VAC, which is V0 minus VC0. So you can see clearly at omega t is equal to 90. So at omega t is equal to 90 to 150, who are conducting? T1 and T2 are conducting. So therefore at omega t from 90 to 150, T1, T2 are going to get conduct. So T1, T2 are going to get conduct in this region. So whenever T1, T2 are conducting, therefore we can say V0 is equal to VAC. So V0 is equal to VAC, which is V0 minus VC0. So at omega t is equal to 90, I want to find what is the value of the output. So at omega t is equal to 90, if you substitute here, which is Vm sin omega t. So Vm sin omega t means 90 minus Vm of sin of omega t minus 240, because VC0 is Vm sin omega t minus 240. So if you substitute here, we are going to get V0 is equal to Vm into 1.5, or simply V0 by Vm is equal to 1.5 per unit. So we can say that at omega t is equal to 90 degree, so the per unit value is 1.5 per unit. So this we have drawn in the graph. Similarly, at omega t is equal to 120, at omega t is equal to 120, I want to find what is the value of this one. So already V0 is equal to Vm sin of 120 minus Vm of sin of minus 120. So because same using the same principle. So now if you solve this one, we are going to get V0 is equal to Vm into root 3, or simply V0 by Vm is equal to root 3 per unit, and this is the maximum value, which is V0 is equal to Vm into root 3, or simply this is called as the peak value of the line voltage, or root 2 into VL. So we have drawn the graph for 90 to 150 also. So I want to find now from 150 to 210 degree. From 150 to 210 degree, so you can see clearly from the graph that T3 and T2 are going to get conduct. So from the graph you can see T2 and T3 are going to conduct. So therefore the output, whenever that T2 and T3 are going to conduct, so therefore simply we can say that V0 is equal to VBC. So V0 is equal to VBC, which is VB0 minus VC0. So at omega t is equal to 150, I want to find what is the value. So V0 is equal to Vm, VB0 is Vm sin omega t minus 120, whereas VC0 is Vm sin omega t minus 240. So in place of omega t substitute 150, and if you solve this one, we are going to get V0 by Vm is equal to 1.5 per unit. So therefore at 150, its value is 1.5 per unit. Similarly, at omega t is equal to 210 degree. At omega t is equal to 210 degree, I want to find what is its value. So we can substitute in this equation, which is V0 is equal to Vm into sin of 210 minus 120 minus Vm of sin of 210 minus 240. So you are going to get 1.5 per unit. So same thing we are going to get again 1.5 per unit. So based on this, we can draw the graph. So based on this, we are going to draw the graph for alpha is equal to 0 degree for any load. If you draw this one, we are going to get in this format. So therefore, from 30 degree to 90 degree, T1, T6 are going to conduct. From 90 to 150, T1, T2 are going to conduct, and from 150 to 210, T2, T3 are going to conduct. So like this, it's going to have a peak value of V0 is equal to Vm into root 3, and the minimum value of V0 is equal to 1.5 into Vm. So minimum value is 1.5 Vm, and the maximum value is root 3 into Vm. So like this, we are going to get, this is the output voltage we are going to get when alpha is equal to 0 for any load. So this is the waveform we are going to get. Each thyristor conducts for 120 degree. So you can see clearly each thyristor is going to conduct for 120 degree. So you can see clearly T1. So if you take only T1, from 30 to 90 degree and 90 degree to 150 degree. So it is conducting from 120 degree. So 150 minus 30 is 120, or simply we can say, so T1 is conducting from 30 degree to 150. So therefore 30 plus 30 plus 30 plus 30, which is 120. So 30 into 4 is 1, 2, 3, 4. 30 into 4 is 120. So therefore each thyristor is conducting for simply 120 degree. So each thyristor is conducting for 120 degree. Each thyristor is conducting for 120 degree. So IT average is equal to, so we can say IT average, as each thyristor is conducting for only 120 degree. So we can assume that the load is highly inductive. So the current is always constant. So therefore I0 into 120 by 360. So this is called as the average value of the thyristor current. So therefore I0 by 3. And if you want to find what is the RMS value of the thyristor current, which is I0 into under root over 120 by 360, we are going to get I0 by root 3, because only for 120 period only each thyristor is going to get conduct. So because of that only we are going to get IT average is equal to I0 into 120 by 360, and IT RMS is equal to I0 into under root over 120 by 360. So like this we are going to get here. So now I want to find what is the source current for any alpha. So now I want to find what is the source current for any alpha. So basically I want to find what is the source current for any alpha I want to figure out. So you can see here, let me assume the current is IA. So you can see clearly IA is called as a source current. IA is called as a source current. The source current can flow only when T1 is conducting or T4 is conducting. So when T1 is conducting, IA is positive, whereas when T4 is conducting, we can say IA is negative. So when T1 is conducting, IA is positive. When T4 is conducting, IA is negative. So either in T1 or T4, we are going to see what is the nature of the IA current. So we are going to see what is the nature of the source current. See, T1 is conducting from. So basically, T1 is conducting from. I have already told you, T1 is conducting from only 30 plus alpha to. So T1 is connecting from only 30 plus alpha to 150 plus alpha. I have already told you. So T1 is always connecting from 30 plus alpha to 150 plus alpha. Whereas T4 is connecting from 210 plus alpha to 330 plus alpha. So therefore, this is the nature of the. So T1 is connecting from 30 plus alpha to 150 plus alpha, whereas T4 is connecting from 210 plus alpha to 330 plus alpha. So this is the range of conduction of the T1 and T4. If T1 is connecting, the source current is positive, and if T4 is connecting, the source current is negative, or simply it is negative of the load current. So plus I0 and minus I0. So now this is in the remaining periods, the remaining times T1 and T4 are not conducting. So simply we can say there at the time it is 0. So in the remaining time both are not conducting. So therefore the source current is equal to 0 at that time. So this is called as a cos square waveform. So the source current in this circuit, which is a cos square waveform, and if you want to find what is the source current average value, which is 0, because positive and negative are going to present, and if you want to find what is the RMS value of the source current, which is I0 into under root over, this is 120 and this is 120, so 240 by 360 degree. So we are going to get I0 into under root over 2 by 3 we are going to get. So now we are going to analyze for alpha is equal to 30 degree at any load. Now we are going to see what is the nature of the output voltage. So for alpha is equal to 30 degree. So when alpha is equal to 30 degree, I have already told you, when alpha is equal to 30 degree, I have already told you T1. Then what is the nature of T1? T1 is going to connect from 30 plus alpha, which is 30 plus 30 is 60. So 60. So you are going to get 30 plus 30 is 60. And we can say T2 will be conducting from. So here simply T2 is going to connect from 90 plus 30, which is 120. So 90 plus 30 is 120. So therefore we can say 60 to 120. So 60 to 120, T1, T6 are going to get conduct. So from 120 to 180. So each thing is 60 degree. So now it is 60 degree. So then T2, T1, again T2, T3, again T3, T4, again T4, T5. So you can see clearly this is from T1, T6. So next is T1, T2, again T2, T3, again T3, T4, again T4, T5. Same phenomena we are going to get. See, whenever T1, T6 are going to conduct, I have already told you the output voltage is equal to, which is VAB. So VAB we are going to get. So like that we are going to draw the graph. So the graph we are going to get in this format. For alpha is equal to 30 degree. So for alpha is equal to 30 degree, we are going to get in this format. So for alpha is equal to 30 degree, we are going to get in this format. So therefore now if alpha is equal to 60 degree, so if alpha is equal to 60 degree any load, again I have already told you, which is T1. So T1 is going to conduct from 30 plus 60, which is 90. So 90. From here it is going to connect. So again same thing, T1, T6, next T1, T2, next T2, T3, again T3, T4, again T4, T5. Same phenomena as the previous one. So if you know the starting point, then you can go for the same way of writing. So see always from here to take the procedure. So T1, T6, T1, T2, T2, T3, T3, T4, T4, T5, T5, T6. Again same from the starting point, T1, T6, T2, T1, T2, T3, T3, T4, T4, T5. Again alpha is equal to 60 means 30 plus 60, which is 90. So again from 90, same procedure, T1, T6, T1, T2, T2, T3, T3, T4, T4, T5. So based on this triggering, try to find what is the output voltage and draw the graph. So you are going to get in this manner. So this is the graph you are going to get. So you can see clearly here, simply we can say that at this range here, the only thing that you need to remember is first you have to know what is the triggering point. First you have to know what is the triggering point of T1. If you know that, then you can go for this simple procedure, which is T1, T6. So again T1, T2. So 30 to 90, 60 degree. So every 60 degree, only two resistors are going to get conduct. So based on this, we are going to draw this one. So alpha is equal to 60 degree, we are going to get this waveform we are going to get. For alpha is equal to 90. So up to alpha is equal to 60, there is no discontinuous mode. Always continuous conversion is going to get possible. Whereas for alpha greater than 60, so let us take alpha is equal to 90 degree for R load. For R load, let me take here R load. So for R load, we are going to get, so alpha is equal to 90 means 90 plus 30. For T1, alpha plus 30 plus alpha, which is 30 plus 90, which is 120. So from 120, go for T1, T6. Then T1, T2. Again to T2, T3. Again T3, T4. Again T4, T5. Again T4, T5. So you can see clearly here, you can see clearly something is very common. But here from 150 to 180. So here actually it has to connect up to 60 degree. So 90, see everything, every two resistors are going to connect from 60 degree. But here only 30 degree they are going to connect. And the remaining 30 they are not going to connect because there will be negative voltage. Whenever there is a negative voltage, as it is a pure resistive load, so therefore current will be negative, but a current cannot be negative in a thyristor. So because of that, all the thyristors are going to get off there. So T1, T6 are going to get off in this time, in the remaining 30 degree. So therefore, if it is open means V0 is equal to 0. So that is the reason it is going to become 0 here. So for alpha greater than 60, only for pure resistive load, it will become discontinuous. Only for resistive load for alpha greater than 60 degree, it is going to become discontinuous mode. So any two thyristors are going to connect for only 60 degree. So any two thyristors are going to connect for only 60 degree for all the cases. For alpha is equal to 90 degree for RL load. For RL load, I have already told you T1 is 30 plus alpha. So 30 plus 90 is 120. So for every 60 degree, they are going to connect. So this is T1, T6. Again, this is T1, T2. Again, this is T2, T3. This is T3, T4. So again, T4, T5. Same thing. But here, then it will be negative value is possible. Here, negative value is possible. So therefore, you can say here T1, T6, T1, T2, T2, T3, T3, T4, T4, T5. So here T5, T6. So this thing is going to get possible. But the only difference is simply here negative is possible because RL load we are going to assume L is huge inductor. So each inductor means current is always positive. So therefore current is always positive means the thyristors are going to connect even for negative voltage. So because of that only we can say that here negative voltage is possible for RL load. So simply we can say that for RL load, irrespective of the alpha, continuous connection is possible. But for resistive load up to alpha is equal to 60 means below 60, yes, continuous connection is possible. But after 60, discontinuous connection is there. So for R load after 60 degree there is a discontinuous conduction. Whereas for RL load there is always continuous connection is possible. See, finally I am telling only one thing which is that you need to remember. See, the output always there are 6 pulses, 1, 2, 3, 4, 5 and 6 pulses. So there are total 6 pulses in the output. So therefore the output frequency is equal to 6 times the supply frequency. And one more interesting this only that you need to remember is two thyristors are going to trigger for only 60 degree. So therefore two thyristors are going to connect for only 60 degree. So from 30 degree to 90 degree. So initially when alpha is equal to 0, so we can say that this is T1, T6 and then T1, T2, again T2, T3, again T3, T4, then T4, T5 and T5, T6. So again same T5, T6. So this is the way that they are going to connect. So only thing is they are going to shift when you are going to vary the alpha. But that is the same procedure. So T1, T6, so T1, T2, T2, T3, T3, T4, T4, T5 and this is T5, T6. So this is the way that they are going to proceed. And they are going to shift. They are going to shift only when the alpha is changing, but everything is same. So they are going to shift by some angle of alpha. If you are going to increase the alpha, and everything is same. So now I have already told you for alpha less than or equal to 60 degree for any load, it is always continuous connection is possible. So therefore, now if you want to find what is the circuit turn off time, means a time for which a thyristor is going to face the reverse or negative voltage, which is 240 minus alpha by omega. So for this time, the thyristors are going to face a negative voltage. So for this much amount of time, they are going to face a reverse voltage. Because each thyristor is going to connect for only 120 degree. So 360 minus 120 is 240. So there is a small amount of angle alpha if alpha is increased. Because here for some amount of time, they are going to face the forward blocking voltage. So therefore 240 minus alpha by omega. So you can see clearly, which is out of 360, 120 degree is for conduction of the each thyristor. So 360 minus 120 is 240. Out of that, alpha is the angle for which these resistors are facing the forward blocking voltage. So therefore now 240 minus alpha. So this much is the angle for which they are going to face the reverse voltage. So 240 minus alpha by omega. So listen carefully. Out of 360, 120 degree is the conduction of each resistor. So therefore the remaining angle is 360 minus 120 is 240. Out of that, alpha is the angle for which they are going to face the forward blocking voltage. So therefore now the remaining angle is 240 minus alpha. In this range of angle, they are going to face the reverse voltage. So 240 minus alpha by omega. So now I want to find what is the average output voltage, which is here. So for average output voltage, which is, if there are 6 pulses, so 1 by 2 pi into 6 into integration of 30 plus alpha to 30 plus alpha to 90 plus alpha. So 30 plus alpha to 90 plus alpha, in this the output voltage is equal to, see, in 30 plus alpha to 90 plus alpha, we can say that T1 T6 are conducting. So whenever the T1 T6 are conducting, so the output voltage is equal to VAB. So output voltage is equal to VAB. So therefore VAB into d theta. But I have already told you VAB is equal to root 3 into Vm into sine of omega t plus 30 degree, as I have already told you. So therefore here we are going to get VAB is equal to root 3 Vm into sine of omega t plus 30 degree. And I have already told you root 3 into Vm is called as the peak value of the line voltage, which is VML. So therefore if you solve this one, we are going to get finally 3 into root 3 into Vm by pi cos phi. So 3 into root 3 into Vm by pi into cos phi. So I have already told you VML is called as a root 3 into Vm, and the line voltage is 1 by root 2 times of VML. So this is the value, this one. So this VML is called as the peak value of the line voltage, and VL is called as the RMS value of the line voltage. For alpha greater than 60, I have already told you only for resistive load there is a discontinuous conduction is possible. So discontinuous conduction is possible only for resistive load. So now we are going to see what is happens for alpha greater than 60. Only we are going to keep the resistive load. So discontinuous conduction is possible. So now I want to find what is the circuit turn of time, is the time for which they are going to face the reverse voltage, which is 180 minus alpha by omega. So this is 180 minus alpha by omega. So 180 minus alpha by omega is the time for which each resistor is going to face the reverse voltage. So 180 minus alpha by omega. So now I want to find what is the average output voltage. So average output voltage is equal to 1 by 2 pi into, as there are 6 pulses, 6 into integration of 30 plus alpha to here 150 only. Here we have to go only up to 150, because here after that it will be 0. So therefore 30 plus alpha to only 150. 30 plus alpha to 150 only we have to go. So therefore 30 plus alpha to 150. Only up to here we should go here, because after that it will be 0. So therefore VAB. So in 30 plus alpha to 150, the resistors which are conducting is T1 and T6. So T1 and T6 are going to conduct in the range of 30 plus alpha to 150. So therefore when T1 and T6 are conducting, so V0 is equal to VAB. So VAB into d theta, which is equal to, so if you solve this one, as VAB is equal to root 3 Vm into sine of omega t plus 30. So if you solve this one, we are going to get finally V0 average is equal to 3 into VML by pi into 1 plus cos of 60 plus alpha. So VML is called as the root 3 into Vm. So therefore here 3 into root 3 Vm by pi into 1 plus cos of 60 plus alpha you are going to get. So this is the equation that you are going to get. Now I want to analyze the source current. As I have already told you, the source current is a cos square waveform. So its equation is equal to sigma n is equal to 135 up to infinity 4 I naught by 4 I naught by n pi into sine of n pi by 3 into sine of n omega t minus n alpha. Whereas in the fully controlled, the expression is sigma n is equal to 135 up to infinity 4 I naught by n pi into sine of n omega t minus n alpha. Whereas for semi-converter, it is sigma n is equal to 135 up to infinity 4 I naught by n pi into cos of n alpha by 2 into sine of n omega t minus n alpha by 2. Whereas for this one, this 3-phase full wave controlled rectifier, here the source current is equal to sigma n is equal to 135 up to infinity 4 I naught by n pi into sine of n pi by 3 into sine of n omega t minus n alpha. The only thing that you have to keep here is extra sine n pi by 3. So this is the only extra term that you should keep, which is sine n pi by 3. So this is the only extra term that you should always keep. So suppose if n is equal to 3, what is going to happen? So 3 by 3 is again cancels, which is pi is equal to 0. If n is equal to, because these are only odd integers, 1, 3, 5, 7, 9. So only odd integers we are going to consider here. When n is equal to again 9, then 3 3 is again 3 by 0. So therefore here we can say that there are no 3n harmonics are absent. So 3n harmonics are basically absent here. So therefore simply we can write, which is sigma n is equal to 6k plus or minus 1 infinity 4 I naught by n pi into sine of n pi by 3 into sine of n omega t minus n alpha. So sine of n 4 I naught by n pi into sine of n pi by 3 into sine of n omega t minus n alpha. So k is ranging from 0, 1 to up to infinity. So simply we can say that there are no 3n odd harmonics are absent because this only contains the odd values. So 3n odd harmonics are going to get absent, like 3, 9, so 15, all these values are going to get absent. So therefore there are no 3n harmonics are absent. So simply we can say 3n odd harmonics are absent in this equation. So now if I want to find what is the fundamental component, I want to know what is the fundamental component of the source current, which is, if you substitute n is equal to 1, we are going to get 4 I naught by pi into sine of pi by 3 into sine of omega t minus alpha. So now fundamental displacement factor is equal to, so this is called as we are going to assume that Va naught is equal to Vm sine omega t. So the phase difference between them, which is alpha. So alpha is the phase difference between the Va naught and the is1 of t, which is alpha. So therefore cos of alpha. So fundamental displacement factor is equal to cos alpha. Whereas distortion factor is equal to the RMS value of the fundamental source current by the overall source current. So here if you want to find what is this RMS value, so therefore here go for the division of root 2 here. So if you do the division of this one, 4 I naught by pi sine of pi by 3 by root 2. So if you do this one, we are going to get this term, which is 2 into root 2 I naught by pi into sine of pi by 3. So we are going to get this expression. Whereas Is RMS value, just now we have already told you, which is I naught into under root over 2 by 3. This is the RMS value of the source current. So if we do a simplification, we are going to get 3 by pi, which is 0.955. So that distortion factor of the source current in the 3-phase full wave control rectifier, which is 0.955. And the input power factor is equal to distortion factor into fundamental displacement factor, which is 3 by pi into cos alpha. So 3 by pi into cos alpha. So if you want to find what is the THD is equal to under root over 1 by g whole square minus 1. So g value, which we already know, which is 0.955, it is independent of alpha. So if you substitute here, we are going to get nearly 31%. So 31% is the THD in this case. So THD in this case, which is nearly equal to 31%, and g is independent of alpha. So Is, I've already told you, the source current is free from odd 3n harmonics. Is basically 3n harmonics or odd components of 3n harmonics. So the source current is free from odd 3n harmonics. See, listen carefully. The source current expression in the full control rectifier, which is simply sigma single phase full wave control rectifier, which is sigma n is equal to 135 up to infinity 4 I naught by n pi into sine of n omega t minus n alpha. Whereas the source current expression in the semiconductor, which is sigma n is equal to 135 up to infinity 4 I naught by n pi into cos of n alpha by 2 into sine of n omega t minus n alpha by 2. Whereas in this 3-phase full converter, which is sigma n is equal to 135 up to infinity 4 I naught by n pi into sine of n pi by 3 into sine of n omega t minus n alpha. And this is free from 3n harmonics or 3n odd harmonics. It is absent. Only odd values it is going to get present. So minimum harmonic present in the source current is fifth harmonic, because you can see clearly here 1, 3, 5. So 1 is the fundamental component, 3 is absent. So minimum harmonic present is fifth one. So minimum harmonic present in the source current is fifth harmonic. So fifth harmonic is the minimum, or we can say it is a starting harmonic present. It is present in the source current. So minimum harmonic present in the source current is fifth harmonic, which is the, so we can say the frequency of that harmonic. The harmonic is called 5 times the fundamental. So therefore 5 times the supply frequency. So that the harmonic of that means the frequency of that harmonic is equal to, that fifth harmonic is equal to 5 into Fs. So 5 is the number into Fs. Fs is the supply frequency. So 5 into Fs. So this is the frequency of that harmonic. So let me do the summary of this 3-phase full converter. So for R load, continuous conduction is possible only up to 60 degree. So therefore alpha can lie from 0 to 60 degree. In this range only continuous conduction is possible, and the conduction of each thyristor is only 120 degree, and the conduction of two thyristors means two thyristors are going to collect for only 60 degree. Only two thyristors are going to collect for only 60 degree. So the average value, which is 3 into root 3 Vm by pi into cos alpha. So this is the called as the average value for continuous conduction. Whereas you can say that this gamma group means conduction of two thyristors. Whereas from 60 to 120, we can say that simply this is a discontinuous conduction is possible. So because of that, now what is the conduction angle of thyristor, which is pi minus alpha. So now pi minus alpha is the conduction angle of the thyristor. Whereas in the previous case, which is 120 degree, but now this is pi minus alpha. So pi minus alpha is the conduction angle of the each thyristor. Whereas the conduction angle of group, the two groups of thyristor, which is 5 pi by 6 minus alpha. So 5 pi by 6 minus alpha is the conduction angle of the group of the thyristors. And the average value also, I have already told you, the average value which is 3 into root 3 Vm by 3 into root 3 Vm by pi into 1 plus cos of 60 plus alpha. So this thing I have already told you. So the average value for alpha greater than 60 means in this discontinuous conduction, the average value of the output voltage, which is 3 into root 3 Vm by pi into 1 plus cos of 60 plus alpha. So you are going to get, this is the expression. RL load, for RL load without freewheeling diode, see, it is going to conduct for all the time. For all the time, it is going to become continuous conduction. So for alpha from 0 to 120 degree, it is going to become always continuous conduction. So the conduction angle of the each thyristor is 120, and the conduction angle of the group of thyristors, which is same 60 degree. So therefore, simply we can say the average value of the output voltage, which is 3 into root 3 Vm by pi into cos alpha. So if you see clearly, see, when alpha is lying between 0 to 90 degree, this value is positive value because of cos alpha. But when the alpha is lying from 90 to 120, the average value is going to become negative. Suppose for RL load with freewheeling diode, suppose if freewheeling diode is going to get present, then what is going to happen? If freewheeling diode is going to present, for alpha ranging from 0 to 60 degree, it is behaving like a R load only. So for alpha is lying between 0 to 60 degree, it is going to behave same as a R load. Whereas from 60 degree to 120 degree, discontinuous conduction is going to get present. So discontinuous conduction is going to get present means it is same as the R load only. So it is same as the R load only, means here it will be 0 for that remaining range. Same, it is going to act like a R load, discontinuous conduction same as the R load. Here also it is going to behave like a same as the R load, but only thing is here in that 0, in that previous R load everyone is off, but here that output voltage 0, here the thyristors, the freewheeling diodes are going to get conduct. So therefore the conduction angle of the each thyristor in this case, which is 5 pi by 6 minus alpha, and the conduction angle of the freewheeling diode here, which is 6 into alpha minus pi by 3. So these are some of the important formulas. From alpha range from 0 to 60 degree, it is same as R load only, continuous conduction mode. But here also it is same like R load, it is same exact like R load, but only thing is here the voltage is 0 in the R load because everyone is off, but here the voltage is 0 because of the conduction of the freewheeling diode. So because of that, the average value is same as this value only, which we have already told you, but discontinuous conduction mode. Whereas this one, the conduction angle of thyristor, which is 5 pi by 6 minus alpha, whereas the conduction angle of the each freewheeling diode, which is 6 into alpha minus pi by 3. So input power factor you can find in also another format, which is input power factor is equal to, see, yes, input power factor is equal to active power by complex power. The active power is P naught and the complex power is input complex power. So therefore P naught by S in. So the output power is equal to V naught average into I naught average, and the complex input power is a three-phase circuit. So root 3 VL IL, or you can say root 3 into VL into IS, because here line current is called as a source current. So therefore here input power factor is the ratio of the active power absorbed by the load by the complex input power, which is the output average power is equal to V naught average into I naught average by the complex input power, which is added a three-phase circuit. So root 3 into VL into IL. Here IL is the line current, or simply it is equal to source current. So here, so if you solve this one, finally we are going to get 3 pi by into cos alpha. So this is another format we can write the input power factor, which is 3 pi by into cos alpha, which is 0.955 into cos alpha. So THD is nearly equal to 31% in this case. So let me tell you some important point here. When alpha is equal to 0, the output maximum value is equal to root 3 times C Vm. Whereas alpha is equal to 30 degree, the output maximum value is root 3 times C Vm. When alpha is equal to 60 degree, the output maximum value is 1.5 times the maximum value. Whereas when alpha is equal to 90 degree, we can say that the output maximum value for R load, which is root 3 by 2 times the Vm. Similarly, for alpha is equal to 90 degree, RL load also, its maximum value is root 3 by 2 into Vm. So these are the important things that you need to remember. So now we are going to learn the three-phase half-wave control rectifier with freewheeling diode. Three-phase half-wave control rectifier with freewheeling diode. Three-phase means we are going to give the three-phase supply. Half-wave means we are going to get 3 pulses at the output. Control rectifier means we are going to use the thyristors. The freewheeling diode means we are going to keep a freewheeling diode across the load. So three-phase half-wave control rectifier with freewheeling diode. So this is the three phases A, B, C, and this is the neutral point, or we can say common point. That is the T1, T2 and T3. So this is the load we are going to keep. Across the load we are going to keep a freewheeling diode. And this is the load voltage V0 and the load current is I0 of T. So and the load current is I0 of T. So I have already told you, see we have already analyzed the circuit without freewheeling diode. But now we are going to keep the extra freewheeling diode to analyze this circuit. So alpha, I have already told you the alpha, you can say thyristor, each thyristor can only on for a period of 120 degree. So therefore the triggering angle of thyristors can range from 0 degree to 120 degree. Only this is the range for which they are going to get on. So now as I have already told you, VAN is equal to, or simply VAN is equal to Vm sin omega t, whereas VBN is equal to Vm sin omega t minus 120 degree, whereas VCN is equal to Vm sin of omega t minus 240 degree. So with the help of these things, we have already drawn the graphs for each and everything, but still again we are going to draw. So here for alpha is equal to 0. For alpha is equal to 0 means I have already told you the triggering angle of thyristor T1, T2 and T3, which is 30 plus alpha, 150 plus alpha, 270 plus alpha. So now is alpha is equal to 0, so T1 is triggered at 30, T2 is triggered at 150 and T3 is triggered at 270. So until T2 is on, so T1 is going to get on. So T1 is on for 30 to 150 and T2 is on for 150 to 270 and T3 is on for 270 to 390. So when T1 is on, V0 is equal to Vn. When T2 is on, V0 is equal to Vbn. And when T3 is on, V0 is equal to Vcn. So they are going to follow this phase voltages. So there we are going to get in this manner. So you can see clearly for alpha is equal to 0, irrespective of load. Load can be anything, whether R load or RL load or any load, we are going to get the output voltage in this fashion. So for this vertical line I have drawn for each and every 30 degree. Suppose if alpha is equal to 30 degree, if alpha is equal to 30 degree, I have drawn for R and RL load. See, 30 degree means now T1 is triggered at 30 plus alpha, so 30 plus 30 is 60. So T1 is triggered at 60 degree. And T2 we are going to trigger at, simply we can say that 150 plus alpha, so 150 plus 30 is 180. And T3 is triggered at, simply we can say 270 plus alpha, so 270 plus 30 is 300. So at 160 degree we are going to trigger the T1, at 180 degree we are going to trigger the T2, and at the 300 degree we are going to trigger the T3. I have already told you when T1 is on, the output voltage is equal to Vgn, and when T2 is on, the output voltage is equal to Vbn, and when T3 is on, the output voltage is equal to Vcn. So they are going to follow these voltages. So like this we are going to get. So this is the shape we are going to get for alpha is equal to 30 degree. Suppose if alpha is greater than 30, if alpha is greater than 30 means there will be discontinuous conduction mode for R load and also RL load. Here because of freewheeling diode only, and because of freewheeling diode is present, so now there is a discontinuous conduction mode for both R load and also RL load also. In the previous case, which is three-phase half-wave control without any freewheeling diode, then here I have already told you up to alpha is equal to 30, it is continuous conduction mode for R load and also RL load. Whereas at alpha greater than 30, it is discontinuous only for R load but not for RL load. But here because of freewheeling diode, it will be discontinuous for both R load and also RL load. Let me take alpha is equal to 60 degree, which is basically for R load we are going to analyze. So when alpha is equal to 60, I have already told you T1 which is 30 plus 60, 30 plus 60 is 90. So T1 is triggered at 90. Similarly, T2 we are going to trigger at 150 plus alpha. So 150 plus 60 is 210 degree. So 210 degree we are going to on the T2, and T3 we are going to on at, which is 270 plus that 270 plus 60. So 270 plus 60, which is 90 degree. So T1 is triggered at 90, T2 is triggered at 210, and T3 is triggered at 330 degree. So therefore simply we can say that here when T1 is on, V0 is equal to VAN, when T2 is on, V0 is equal to VBN, and when T3 is on, V0 is equal to VCN. So it is going to follow this one. But here after 180, see, in the original case the graph VN is negative, but here it negative cannot be possible. Negative cannot be possible because if V0 is negative, then definitely freewheeling diode is going to get conduct here. So because of that, the freewheeling diode is going to conduct in this region. So the freewheeling diode is going to conduct in this region, so which is from 180 to 210. Similarly, T2 is triggered at 210. So therefore simply we can say that here because of T2 here from, so when T2 is on, V0 is equal to VBN. Again at 300, VBN is negative. So VBN wants to be negative. Whenever VBN is negative, I have already told you V0 cannot be negative for R load. If it is a negative, then definitely freewheeling diode is going to get conduct. But actually it won't happen negative. If it is negative, so current is also negative. So thyristor current cannot be negative. So because of that, it will be open, or simply we can say that all thyristors are open in this period. So all thyristors are open in this 180 to 210 degree. Similar T3 also, when T3 is on, V0 is equal to VCN. So therefore here we are going to follow the VCN, but here VCN is negative. If VCN is negative, then definitely the current is also negative. So thyristor current cannot be negative direction. So because of that, everyone is open. So everyone is basically open in this period. So everyone is going to open in this period. So from 180 to 210 and 300 to 330 and 60 to 90, everyone is open. So everyone is, every thyristor is open. Here freewheeling diode is not conducting in these regions. There is no way of freewheeling diode conduction in this 0 period. Whenever the voltage is equal to 0, here everyone is off, but it is not a conduction of the freewheeling diode. But if you take the RL load for alpha is equal to 60 degree, so same procedure for same as the previous one, but here it will be negative without freewheeling diode. But here because there is a freewheeling diode, as V0 tries to be negative, so freewheeling diode is going to get conduct. So therefore voltage is equal to 0. So here freewheeling diode is going to get conduct, but in the previous case there is no conduction of freewheeling diode. So freewheeling diode is going to conduct whenever the voltage want to be negative. So because of that, the voltage will be 0. So this is the way that I want to tell you that for 3-phase half-wave control rectifier with freewheeling diode, for alpha greater than 30 degree, there is discontinuous conduction mode for R load and also for the RL load. So this is the point that you need to remember. So let me do the analysis of this circuit. I have already told you for 0 less than or equal to alpha less than or equal to 30 degree, for both R load and also RL load, it is a continuous conduction mode. Already we have did the average value, which is V0 average is equal to 1 by 2 pi into 3 times of integration of 30 plus alpha to 150 plus alpha. In that period, T1 is conducting, so therefore the output voltage is equal to VAN, so which is Vm sin theta into d theta. So if you do this one, we are going to get simply 3 into root 3 Vm by 2 pi into cos alpha. So 3 into root 3 Vm by 2 pi cos alpha is the correct solution of this question. Or we can say that this is the V0 average of this sum. So whereas we can say that in this period, each thyristor is conducting for a period of 120 degree. So the conduction angle of each thyristor is 120 degree. And there is no freewheeling diode conduction. So it is not at all conducting in this region. So the conduction of the freewheeling diode in this range of alpha is 0. So if we want to find what is the IT average, so each thyristor is conducting for only 100 degree, means in the remaining time it is off. So therefore in the off period the current is equal to 0. So therefore now I0, let me assume the load is highly inductive. So because of that the current is constant value. So I0 into 120 by 360, which is I0 by 3. So if we want to find what is the RMS value of thyristor current, which is I0 into under root over 120 by 360. So you are going to get I naught by root 3. So for alpha lying between 30 degree to 100 degree. So for alpha lying between 30 degree to 120 degree, for R load and RL load, it is a discontinuous conduction mode. So it is a discontinuous conduction mode in this range. So therefore now V naught average will be, I already told you, now V naught average will be, which is into 1 by 2 pi into 3 times of integration of 30 plus alpha to, simply we are going to get up to 180 only. So 30 plus alpha to up to 180 only, we have to do the integration. So in this region of 30 plus alpha to 180, T1 is conducting. So therefore, whenever the T1 is conducting, the output voltage is equal to, simply we can say VAN, which is Vm sin theta into d theta. So if you solve this one, we are going to get 3 Vm by 2 pi into 1 plus cos of alpha plus 30 degree. So this is the value of the output average voltage that you are going to get. And if you want to know what is the conduction angle of the thyristor, so what is the conduction angle of the thyristor? So I have already told you, it is thyristor means T1 is connecting from only 30 plus alpha to 180. So therefore the conduction angle of the thyristor is equal to 180 minus of alpha plus 30. So you are going to get 5 pi by 6 minus alpha. So this is the range of the conduction angle of the east thyristor. And if you want to know what is the conduction angle of the freewheeling diode, so if you want to know what is the conduction angle of the freewheeling diode, see the freewheeling diode is going to conduct, see for R load and RL load. See, this is an important point. For R load and RL load, for R load and RL load, always for R load and also RL load, for alpha greater than 30, freewheeling diode is always going to get conduct. The freewheeling diode is always going to get conduct irrespective of the R load or RL load. Always the freewheeling diode is always going to get conduct. So therefore the conduction angle of the diode is equal to, simply we can say that here alpha plus 30 degree plus 120 degree minus of 180 degree into 3. So simply we can say that alpha plus 30. So alpha plus 30 means, see I am trying to find what is the range for T1, the T1 range, which is alpha plus 30 plus 120 minus 180. So this is the range for which it is trying to conduct for T1, but it is for 3 cases, so into 3. So we are going to get finally 3 into alpha minus pi by 6. So alpha plus 30 plus 120 minus 180 means this is the range for which only for T1 case the freewheeling diode is going to conduct in this range. But there are 3 thyristors, so you have to go for 3 times to get the value of the overall conduction angle of the freewheeling diode for the both R load and also the RL load. So which is 3 times of alpha minus pi by 6. So now if you want to find what is the IT average, so IT average is equal to I naught into, it is connecting for a period of this period, so 5 pi by 6 minus alpha by 2 pi, and IT RMS is equal to I naught into under root over 5 pi by 6 minus alpha by 2 pi. So if you want to find what is the freewheeling diode average current, which is I naught into, this is the conduction, so 3 into alpha minus pi by 6 by 2 pi, and I freewheeling diode RMS value is equal to I naught into under root over 3 into alpha minus pi by 6 by 2 pi. So this is the conduction, or we can say the average value of thyristor current, average value of the freewheeling diode, RMS value of thyristor current, and the RMS value of the freewheeling diode current. So these are some of the important expressions which are regularly asked in the examination. So let me tell you some important point here. As I have already told you here, 60 to 90 degree and 100 to 210 degree and 300 to 330 degree. Here freewheeling diode is going to get conduct, because when the input voltage wants to be negative, automatically the freewheeling diode is going to get conduct. So because of that, here the freewheeling diode is going to get conduct here. So we can say yes, there is a conduction of freewheeling diode here. So we can say that the freewheeling diode is going to conduct for alpha greater than 30 degree, no matter whether it is R load or RL load, always the freewheeling diode is going to get conduct here. So now we'll discuss the new concept, which is the effect of source inductance. So what is the effect of source inductance? Now we are going to see. See, this is called as this is basically a single phase source, thyristor, and also there is a load, and here there is a freewheeling diode. So now here basically now because of this source inductance, a source is going to have small amount of inductance. Let me take LS. So now we are going to analyze this circuit. So the load voltage is V naught of t and the load current is I naught of t, and the current in the freewheeling diode is IF of d, and the current in the thyristor is I of t. So this is called as a one pulse converter. So because already we know that only in the output there is a one pulse, only one pulse. That is the reason we say it is a one pulse converter. So now let us analyze these diagrams. So let me assume the source voltage is Vs of t is equal to Vm sin omega t. So this is the graph we are going to get, which is for 0 to pi positive pulse and pi to 2 pi negative pulse. So now suppose there is no source inductance. So without source inductance, already we have drawn the graphs of the output voltage, thyristor current and the freewheeling current. So these are the three graphs without having any source inductance, without having any effect of source inductance. See, I've already told you at alpha we are going to trigger the thyristor. Here at alpha, if you are going to trigger the thyristor, means the thyristor is going to get on. So whenever the thyristor is on, so output voltage is equal to source voltage. So output voltage is going to follow the source voltage up to pi. After that, voltage try to be negative. If voltage is try to be negative, means freewheeling diode is going to get conduct. So therefore output is equal to 0. So therefore your output voltage will be 0 after that, because only for alpha to pi, we can say that only for alpha to pi the thyristor is conducting. In the remaining range of pi to 2 pi, the freewheeling diode is going to get conduct. The freewheeling diode is going to get conduct. That is the meaning of this one. So now let me assume the load is having a constant current. So load is having a constant current. So therefore simply from 0 to pi. So from 0 to pi also, see, as the load is having a huge amount of current. So as the load is having huge amount of current, definitely here there will be a freewheeling diode is conducting from 0 to alpha, and from alpha to pi the thyristor is conducting, and from pi to 2 pi again freewheeling diode is going to get conduct. So based on this we are going to draw the thyristor current and also the freewheeling diode current. We have assumed that the load current is a constant current, because the load we are going to assume it is having a huge value of inductance. So because of that we can say simply that here, so from alpha to pi, the thyristor is going to conduct. So it's going to have a value of the thyristor current is equal to load current of I naught value. Whereas from 0 to alpha and pi to 2 pi, the freewheeling diode is going to get conduct. So because of that, simply we can say that this is the diagram of the freewheeling diode current, which is I naught here and here also I naught. So this is the graphs of the output voltage, thyristor current and the freewheeling diode current without any source inductance. So now we are going to draw with the effect of source inductance. So if source inductance is there, then what is the nature of the thyristor current, freewheeling diode current, and then we are going to draw the output voltage. See, because of inductor, in an inductor current cannot change instantaneously. As current cannot change instantaneously, so it will slowly rise. But here there is an ideal, it has raised suddenly from 0 to some non-zero value. Again suddenly dropped from non-zero value to 0. But because of source inductance, it can only go in a very slow manner. So now let us take the ID, the thyristor current. So up to alpha it is 0. After that it is going to slowly increase. Let me assume some alpha plus mu. So it is going to slowly increase up to alpha plus mu. Again up to pi it will be same I naught. Again suddenly it cannot become 0. So therefore again pi plus mu. So for again it is going to small decrease up to pi plus mu. So small increasing from alpha to alpha plus mu, small decreasing from pi to pi plus mu. Again we can say the freewheeling diode current. So from 0 to alpha its value is I naught. After that alpha to alpha plus mu it is going to slightly decrease, and again up to pi it is 0. After that it cannot become suddenly increase. So from pi to pi plus mu it is going to slowly increase, and then it is going to become the same value I naught. So because of inductance, because of source inductance, so we can say that because of source inductance the current cannot change instantaneously. So current cannot change instantaneously because of this source current, because of the source inductance. So this is the nature of the thyristor current and also the freewheeling diode current. So with the effect of the source inductance. So now you can see clearly from alpha to alpha plus mu and pi to pi plus mu. So alpha to alpha plus mu, here both the freewheeling diode and also the thyristor are conducting. So if both are conducting, then what is going to happen? If both are conducting means simply we can say the output voltage is equal to 0 in that case also. So from alpha to alpha plus mu, the voltage will be 0. Similarly, from pi to pi plus mu also, both are conducting and the output voltage is again 0. But you can see if you compare with the original graph, so now here from alpha to alpha plus mu, it is a non-zero value, but here it is a 0. So because of that thing, we can say that now the output voltage value is going to get decreased. So the output average value is going to get decreased. So this is a thing that you need to remember. So from alpha to alpha plus mu, the value became 0. So therefore, overall average value of the output voltage is going to get decreased. So because of source inductance, the average value of the output voltage is going to get decreased. Where mu is called as the commutation angle, or simply we can say that for overlap, see mu is called as the overlap angle. Mu is called as the overlap angle means in this period, both the thyristor and also diode are going to get conduct, because in this circuit there are two switching devices. So therefore, the devices are going to connect in this period. So now we are going to do the analysis of this circuit. So during alpha to alpha plus mu. So during alpha to alpha plus mu, here both the thyristor and also the diode are on. The freewheeling diode and the thyristor both are on. So thyristor and the freewheeling diode are on. So therefore, when both are on, definitely V0 output voltage is equal to 0. So now, what is the conduction angle of thyristor without LS? Without LS, it is connecting only from alpha to pi. So therefore, pi minus alpha is the conduction angle of thyristor without source inductance. But with source inductance, the thyristor is conducting from alpha to pi plus mu. So therefore, the thyristor is now conducting from alpha to pi plus mu. So therefore, pi plus mu minus alpha. This is called as the conduction angle of the thyristor with the source inductance. So now I want to find what is the average value of the mu output voltage, which is 1 by 2 pi integration of alpha plus mu to pi Vm. So V0 of t is nothing but here in this case from alpha plus mu to pi, here thyristor is conducting. So when thyristor is conducting, the output voltage is equal to source voltage. So simply we can say that it is equal to Vm sin theta into d theta. So Vm sin theta into d theta. So therefore, if you solve this one, we are going to get Vm by 2 pi into 1 plus cos of alpha plus mu. So Vm by 2 pi into 1 plus cos of alpha plus mu. Simply we can say that Vm by 2 pi into 1 plus cos of alpha plus mu. So Vm by 2 pi into 1 plus cos of alpha plus mu. So this is the call as the average value of the new output voltage with the source inductance. See, we have assumed that in this period the thyristor is on. So in this period the thyristor is on. So therefore freewheeling diode is off. So but we have assumed that the load is having a constant current. So constant current means the voltage drop across the LS source inductance is 0, because as I0 is constant, so IT is equal to I0 in this case. So therefore dIT by dt is equal to 0. So therefore voltage drop across the LS is equal to 0. So therefore whatever the output voltage is equal to source voltage. So based on this, we are going to get this expression, which is Vm by 2 pi into 1 plus cos of alpha plus mu. So this is the average value of the output voltage with the source inductance. Suppose if you are not going to keep the source inductance, then V0 average, which is old value, is equal to 1 by 2 pi integration of alpha to pi Vm sin theta d theta is equal to, which is Vm by 2 pi into 1 plus cos alpha. So this is the value of the without LS. So we can say clearly the average value of the output voltage in the old is always greater than the average value of the output voltage of new value. So because here there is a lot of amount of area, but here the area is less, because of this its value is lesser. So if you want to find how much is the amount of change in the average value of the output voltage, so the amount of change in the average value of the output voltage is equal to V0 old minus V0 new, because V0 old is greater than the V0 new. So if you do the subtraction of this one, V0 old is Vm by 2 pi into 1 plus cos alpha, whereas V0 new is equal to Vm by 2 pi into 1 plus cos of alpha plus mu. So based on this, we are going to get finally Vm by 2 pi into cos alpha minus cos of alpha plus mu, where mu is called as the overlap angle. So as overlap angle increases, we can say that the average value of the output voltage of the new value goes on decreases. So therefore their difference will increase. So therefore as mu increases, we can say that this value increases. As mu increases, this value increases. So during alpha to alpha plus mu, so during alpha to alpha plus mu, I have already told you both both the resistor and also the fluid diode is on. So therefore, we can say simply if you apply the KVL, then whatever the supply voltage is equal to voltage drop across the inductor. So VL is equal to Vm sin theta, because whatever the voltage across the inductor is equal to voltage across the source, which is VL is equal to Vm sin omega t, whereas VL is equal to L into dit by dt, because in that time the current through the inductor is thyristor current only. The current through the inductor at the time is the thyristor current. So therefore di of t by dt is equal to Vm sin omega t. So now I will take dt here and L downward. So we are going to get dit is equal to Vm by L into sin omega t into dt. So now I am going to do the integration of the thyristor current in the range from alpha to alpha plus mu. So you can see clearly from the graph, from alpha to alpha plus mu, the thyristor current is changing from 0 to I0. So the current is changing from 0 to I0. The thyristor current is changing from 0 to I0 for a time of t is equal to alpha by omega to alpha plus mu by omega. So for a time of alpha by omega to alpha plus mu by omega, the current is changing from 0 to I0. So if you do the simplification, we are going to get finally, which is I0 is equal to Vm by omega Ls into cos alpha minus cos of alpha plus mu. So here simply now we can compare this one with, suppose if you multiply I0 by, see if you take omega Ls to the this side, we are going to get I0 omega Ls by 2 pi. If you do this one, we are going to get delta V. So delta V we are going to get same thing, we are going to compare these two equations. So finally delta V is equal to omega means 2 pi f. So 2 pi cancels. So finally delta V is equal to f into Ls into I0. So the amount of change in output voltage means the amount of change in output voltage, average value of the output voltage is equal to f into Ls into I0, where f is the supply frequency and L is the source inductance and I0 is the load current. We have assumed the load is a huge inductive, so its current is constant. So f Ls I0. So f Ls I0 is the value of the average value of the output voltage, or we can say the amount of change in the average value of the output voltage, which is f Ls I0 is the formula of this one. So now we are going to learn about the what is the effect of source inductance on this 2 pulse converter. So previously we have learned what is the effect of source inductance on the 1 pulse converter, but now we are going to see what is the effect of source inductance on the 2 pulse converter. So this is a 2 pulse converter, means in the output there are 2 pulses. So this is called as the source voltage, and this is basically full bridge rectifier, full bridge single phase full bridge rectifier, full bridge control rectifier. So therefore this is the circuit you are going to get, but only thing is we are going to keep a source inductance. So now we have to analyze what is the waveforms of the output voltage and everything we need to see here. So therefore now here the thyristor T1, T2, T3 and T4, and this is the source current Is and the source inductor is Ls, and this is the output voltage and the output current. So now we are going to analyze this circuit. See, as a source voltage, I have already told you the source voltage is equal to Vm sin theta. So Vm sin omega t. So from 0 to pi there is a positive pulse, and from pi to 2 pi there is a negative pulse. So this is the graph we are going to get. So now here what I am going to do basically, so without Ls, I am going to try to draw what is the graph of the output voltage and the source current. So what is the output voltage and the source current? Now I am going to draw without the effect of the source inductance. So without the effect of the source inductance, I am trying to draw what is the value of the, what is the graph of the output voltage and also the source current. I have assumed that the load is highly inductive, so the load current is always constant with respect to time, because we are going to assume the load inductance is very high. So I have already told you, see at alpha we are going to trigger T1, T2, whereas at pi plus alpha we are going to trigger T3, T4. So from alpha to pi plus alpha, T1, T2 are going to trigger. If T1, T2 are triggered, so therefore the output voltage is equal to source voltage, so it is going to follow the source voltage. Whereas from alpha plus pi to 2 pi plus alpha, we are going to trigger the T3, T4. So therefore they are going to get on. So therefore whatever the output voltage is negative of the source voltage, so we are going to get negative of the source voltage we are going to get in this region. So T1, T2 are going to connect from alpha to pi plus alpha, whereas T3 and T4 are going to connect from pi plus alpha to 2 pi plus alpha. So by this we are going to get, this is the output voltage we are going to get. So if you want to find what is the average value of this graph, which is Vm by 2 pi into 2 Vm by pi into cos alpha. So 2 Vm by pi into cos alpha is the average value of this graph. So now I want to find what is the source current. What is the source current? I've already told you when T1, T2 is conducting. When T1, T2 is conducting, whatever the source current is equal to load current. So here from alpha to pi plus I, whatever the source current is equal to load current in this range. Whereas from pi plus alpha to 2 pi plus alpha, T3, T4 are conducting. So therefore the source current is negative of the load current. So source current is negative of the load current we are going to get. So this is the graph we are going to get for the output voltage and also the source current. So now what we are going to do simply is here with the help of means if you are going to keep the source inductance, now we are going to draw what is the graph of the output voltage and also the source current we are going to draw. So you can see clearly now what is going to happen is the source current cannot changes instantaneously because there is a we can say as the source current cannot changes because there is a inductor here. So inductor because the source current should pass through inductor. So therefore the IS cannot changes instantaneously. Means there will be no sudden rise or no sudden drop. So now here what is going to happen is, so you can see clearly from minus I naught it is going to go slowly. It is going to slowly increase. So from alpha to alpha plus mu it is going to slowly increase. Again from pi plus alpha to pi plus alpha plus mu. So from pi plus alpha to pi plus alpha plus mu it is going to slowly decrease. So you can see clearly in this range, all the thyristors are conducting here. So from alpha to alpha plus mu and pi plus alpha to pi plus alpha plus mu, all the thyristors means all the devices in this are going to get conduct. So if all are conducting in this region, because here ideally I have already told you from 0 to alpha T3 T4 connecting. So from alpha to pi plus alpha T1 T2 connecting. So because of this amount of change, so we can say each and every thyristor is conducting in this region. So everyone is going to get conduct in this region. If everyone is conducting, then definitely we can say that if everyone is conducting, simply we can see that the output voltage is equal to 0. So the output voltage will be 0 here, and here also the output voltage will be 0. So this is the thing. This is called as a new way of the getting the output voltage. So simply we have to keep here 0, and here also we have to keep it 0. So this is a graph we are going to get finally. So from here like this 0, again it is coming up to here, again it is 0, again it is coming like this. So there is the area was decreased. So we can say now the average value of the new output voltage is going to get decreased because in this overlap angle all the thyristors are conducting. So therefore the output voltage will be 0 here. So because of that the overall area decreases. As overall area decreases, the output average value goes up, decreases. So let me do the analysis of the circuit. See, during alpha to alpha plus mu, everyone is conducting. All the thyristors are conducting. So all the thyristors are conducting because here the source current is it cannot changes instantaneously. So because of this reason only, each and every device is going to get conduct. So from alpha to alpha plus mu, all thyristors are conducting. So therefore now here without LS, what is the conduction angle of thyristor? See, T1 and means T1 is connecting from alpha to pi plus alpha. So if you do the difference of this one, pi plus alpha minus alpha, you are going to get the conduction angle of each thyristor is equal to pi without source inductance. But if you want to find what is the conduction angle of the thyristor, the conduction angle of the thyristor when source inductance is present, which is, see, you can see clearly that T1 is conducting from alpha to pi plus alpha plus mu. So we can say that T1 is connecting from alpha to pi plus alpha plus mu. So if you do the difference, we are going to get pi plus alpha plus mu minus alpha. We are going to get pi plus mu. So this is the conduction angle of the each thyristor we are going to get, which is pi plus mu with LS. So it was increased. The conduction angle was increased by a factor of mu by adding the source inductance. So now what is the average value of the output voltage? Old value means without source inductance, which is 2m by pi into cos alpha. Simply if you want to do the principle, which is 1 by 2 pi, 2 times of integration of alpha to pi plus alpha Vm sin theta into d theta. So if you do this one, we are going to get 2Vm by pi into cos alpha. But if you want to find what is the average value of the output voltage mu value, which is 1 by 2 pi, 1 by 2 pi into 2 times of integration of alpha plus mu to pi plus alpha Vm sin theta into d theta, because in this region T1 T2 are connecting. So as T1 T2 conducts, so the output voltage is equal to source voltage. As I have already told you, when T1 T2 are connecting, the load current is always constant. The source current is also equal to I0. So whenever the source current is equal to I0, the voltage drop across the inductor is zero because current is constant. So whatever the output voltage is equal to voltage across the source. So we are going to get finally Vm by pi into cos alpha plus cos of alpha plus mu. So Vm by pi into cos alpha plus cos of alpha plus mu. So this is the value we are going to get. So Vm by pi into cos alpha plus cos of alpha plus mu. So now already old value is always greater than the new value. So therefore if you want to know what is the amount of change in the average output voltage, which is old value minus new value. So if you do this one, we are going to get Vm by pi into cos alpha minus of cos of alpha plus mu. So Vm by pi into cos alpha minus of cos of alpha plus mu. So this is the change in the average value of the output voltage we are going to get. So during alpha to alpha plus mu, each thyristor is conducting, means all the thyristors in the circuit are going to get conduct. So therefore we can say that if all are conducting, we can say simply that V0 is equal to 0. So therefore whatever the source voltage is the voltage drop across the source inductance. So therefore VL is equal to Ls into di by dt is equal to Vm sin omega t. The current to the inductor is equal to source current. So therefore di is equal to Vm by Ls into sin omega t into dt. So now you can see the source current is changing from minus I0 to I0. The source current is changing from minus I0 to I0 in a given time period of t is equal to alpha by omega to alpha plus mu by omega. So if this is simplification, finally we are going to get 2 I0 is equal to Vm by omega Ls into cos alpha minus of cos of alpha plus mu. So I0 is equal to Vm by 2 omega Ls into cos alpha minus of cos of alpha plus mu. So if you do a further simplification, 2 omega Ls into I0 by pi, then we are going to get which is equal to delta V0. So delta V0. So therefore omega is equal to 2 pi f. So if you solve this one, we are going to get 4 FLS I0 is equal to delta V0. So the simple formula which we are going to get, delta V0 is equal to 4 FLS into I0. 4 FLS into I0. So but in the previous case we have got which is delta V is equal to FLS I0, whereas here we got 4 FLS I0. Means that simply the number of thyristors we have to keep here. This number is going to tell you the number of thyristors you should include here. So in the previous case there is only one thyristor, so which is 1 into FLS I0, whereas here there are 4 thyristors, so therefore you have to keep here 4. So delta V is equal to FLS I0 in the previous case, but here which is delta V0 is equal to 4 FLS I0. So this is a way that you need to remember. Now we will do a special case in this circuit. So in this 2-pulse converter, we are going to consider a special case. For diode bridge means here just we have to replace alpha is equal to 0. Then we are going to get that whole one is going to convert into a diode bridge full bridge rectifier. So diode full bridge rectifier. So I have already told you what is the conduction angle of the thyristor. The general formula I have already told you with the effect of source inductance, which is pi plus mu. But here now we are going to replace thyristor by diode because we are going to consider alpha is equal to 0. So therefore we can say the conduction angle of the diode is equal to pi plus mu because it is independent of alpha. So this is pi plus mu. And if you want to find what is the average output voltage, the general average output voltage with the effect of source inductance, which is Vm by pi into cos alpha plus cos of alpha plus mu, but alpha is equal to 0. So therefore if you substitute here, finally we are going to get 1 plus cos of mu. Sorry, see the amount of change in average voltage. So this is called as a change in average voltage. The amount of change in average voltage is equal to Vm by pi into cos alpha minus of cos of alpha plus mu. As alpha is equal to 0, we are going to get Vm by pi into 1 minus cos mu, where mu is called as the overlap angle. And also the amount of change in average value of the output voltage is equal to 4 FLS I0. So therefore now what is the fundamental displacement factor? The fundamental displacement factor without source inductance. So the fundamental displacement factor without source inductance is equal to the means without LS means without source inductance is equal to, simply we can say that, see, I have forgotten to say this important point, which is the fundamental displacement factor. The fundamental displacement factor without source inductance is, which is cos of alpha. This point that we have already studied. The fundamental displacement factor without the source inductance is cos alpha. So by introducing the source inductance, or we can say by introducing the source inductance means with LS, the fundamental displacement factor will be cos of alpha plus mu by 2. So cos of alpha plus mu by 2. So the fundamental displacement factor without the source inductance is cos of alpha, whereas with source inductance is cos of alpha plus mu by 2. Then what is going to happen? As frequency increases, or the source inductance increases, or the load current increases, then definitely out of this, if any one parameter increases, then delta V naught increases. As delta V naught increases means, simply we can say that mu is increasing, means the overlap is increasing. As the overlap angle increases, so therefore we can say that simply it is independent of supply voltage. Means here this mu is going to depend only on these three parameters, but it is independent of the magnitude of the supply voltage. So if out of these three parameters, if any parameter increases, then definitely delta V naught increases. As delta V naught increases, mu increases, and this mu is, the variation of mu is independent of the supply voltage, independent of the magnitude of the supply voltage. It only depends upon only these three parameters, which are supply frequency, source inductance, and the load current. Only on these three parameters the delta V is independent. If delta V is independent, definitely we can say here the mu is also independent only on these three parameters, but it is independent of the supply voltage. So let me tell a special condition for diode bridge. For diode bridge means we are going to assume here it is a alpha is equal to 0. For alpha is equal to 0, this full controlled bridge is going to convert into a full diode bridge rectified. So therefore I have already told you the conduction angle of thyristor is equal to, with LS is equal to pi plus mu. It is independent of alpha. So therefore the conduction angle of thyristor in this case is pi plus mu. Whereas if you want to know what is the amount of change in the average output voltage, which is Pm by pi into cos alpha minus cos of alpha plus mu, as alpha is equal to 0, we are going to get Pm by pi into 1 minus cos mu. And as I already told you, the amount of change in average output voltage is equal to 4 FLS I naught. 4 FLS I naught is the amount of change in the average output voltage. And if you want to find what is the fundamental displacement factor without source inductance is cos alpha, and if you want to find with source inductance, so with source inductance is equal to cos of alpha plus mu by 2. As alpha is equal to 0, we are going to get cos mu by 2. So simply we can say that, so in this special condition, the fundamental displacement factor without source inductance is equal to cos alpha. As alpha is equal to 0, we are going to get 1. Whereas fundamental displacement factor with source inductance is equal to cos of alpha plus mu by 2. As alpha is equal to 0, we are going to get cos of mu by 2. So this is some of the important special conditions of this 2-pulse converter. Now we have discussed the single pulse converter and 2-pulse converter. So now we are going to study directly 6-pulse converter. So for the 6-pulse converter, we are going to see what is the formulas we are going to get with the effect of source inductance. Now we are going to study. So here I naught is equal to VML by 2 omega LS into cos alpha minus cos of alpha plus mu, where VML means the peak value of the line voltage, which is root 3 into Vm. And if you want to know what is the new value of the average output voltage, which is 3 VML by 2 pi into cos alpha plus cos of alpha plus mu. And if you want to know what is the average output voltage of the old value, means without source inductance, which is 3 VML by pi into cos alpha. So 3 VML by pi into cos alpha without source inductance. So now you want to find, if you want to find what is the amount of change in the output average value of the output voltage, which is old value minus new value. Because of new value, the value decreases. So old value minus new value. So if you do this one, we are going to get 3 VML by 2 pi into cos alpha minus cos of alpha plus mu. So if you do some simplification, we are going to get finally is equal to 3 omega ls I naught by pi. So if omega is equal to 2 pi, so finally we are going to get 6 FLS I naught. I have already told you in the 6-pulse converter there are 6 thyristors. So therefore the amount of change in average output voltage is equal to 6 FLS I naught. This number indicates the number of thyristor present in the circuit. So therefore, this is the way that you need to remember. And the fundamental displacement factor with the effect of source inductance is equal to. So with the effect of source inductance is equal to cos of alpha plus mu by 2. But if you want to know what is the fundamental displacement factor without source inductance, then without source inductance means it is equal to cos alpha. With source inductance it will be cos of alpha plus mu by 2. It's a very important point. So with source inductance means cos of alpha plus mu by 2. Without source inductance means it is cos alpha. That is the thing that you need to remember.